What if a stone the size of a cathedral arrived at the doorstep of the sun, bearing the faint fingerprints of another world? The question sits like a cold coin in the palm, simple, heavy, and impossible to ignore. It reframes everything that has ever been assumed about isolation, about the neatness of cosmic loneliness. When 3i last appeared on humanity's instruments, it did not simply arrive as another rock on an old trajectory. It arrived as a question wrapped in velocity, an object that had crossed the dark distances between stars and carried with it the peculiar accent of somewhere else. 3i Atlas was not like the familiar rubble that circles the sun. Typical asteroids, comets, and fragments within the solar system speak the language of local history: slow, gravitationally domestic orbits, surfaces weathered by the steady, patient sputter of micrometeorites and solar wind, icy visitors that develop comas and tails as they warm on their way inward. They are, in a sense, family. 3i Seklas announced from the first faint arc of its trajectory that it belonged to another lineage. Its inbound path could not be reconciled with capture by the sun's gravity alone. Its speed, direction, and the slight, almost maddening discrepancies in brightness painted a picture of an interstellar traveler, a wanderer that had threaded its way across the spaces between stars, and then, for a brief while, threaded through the solar system's outskirts like a moth passing a lamplight on an endless night. It arrived with the rough signature of the unknown. The change in brightness as it tumbled suggested shapes that did not conform to the tumbling, rounded profiles of many asteroids. Spectra hinted at compounds not readily matched with the typical inventory of solar system rocks. And then there were the subtler anomalies, microaccelerations that did not fully obey radiation pressure models, faint alkali lines that seemed factionally shifted, a small but persistent whisper of non-gravitational forces. Alone, each clue might have been dismissed as the stubbornness of measurement. Together, they built a case that resistance to easy explanation was the object's default state. The possibility that 3i Atlas was an emissary from distant epochs of cosmic history, a fragment from a planetary surface that had been flung free by some violent event, a pebble from a protoplanetary disk born under different suns, reshaped the imagination. Interstellar objects are, in the broadest sense, time capsules. Travel through interstellar space is slow, cold, and merciless. Surfaces accumulate scars from cosmic rays and suffer the brittle erosion of absolute cold, but they also preserve. In the same way that a piece of bone can whisper the diet of a vanished animal through isotopic ratios, the mineralogy and chemistry of an interstellar rock can encode a distant environment, the kinds of rocks that built its parent world, temperature range it once experienced, the presence or absence of liquids, and even episodes of irradiation or atmospheric chemistry it once saw. This was the first layer of the question. What stories did 3i Atlas carry in its rock? The second, more disquieting layer asked what stories it might erase or reveal about Earth's own fragile memory. Human history is an instant within Earth's geological biography. The strata that record civilizations, cities, monuments, radio transmissions, plastic detritus, are like a thin patina on a much older surface. Deep time is indifferent. It buries and grinds, reducing architectures and languages to chemical traces, bones to geochemical anomalies. If 3i Atlas bore evidence of technologies or structures that had existed beyond the solar system, that evidence might be more legible than anything humans could leave for their far-distant descendants. Conversely, if there had been previous bursts of intelligent activity on Earth or nearby, time has already proven itself efficient at erasure. The mind that contemplates 3i Atlas cannot help but feel both hopeful and bereft, hopeful at the prospect of reading an external archive, bereft because Earth's own ledger is so impoverished. To stand under this idea is to feel small and temporary in a way the medieval sky could never convey. Human civilizations have been a blink. Continents have been a slow, churning drama. Mountains grow and then vanish. Oceans open and close like folding hands. If a wandering fragment from another star system can preserve chemical anecdotes for millions, perhaps billions of years, then the contrast between what persists and what is transient becomes acute. The rock is a messenger and a mirror. It tells of other worlds while reflecting back the ephemeral nature of human endeavor. There is a technical, almost ritualistic choreography to how a moment like this unfolds. Instruments trained for centuries-old tasks, telescopes designed to map distant galaxies, spectrometers tuned to measure starlight are repurposed in a matter of hours to interrogate the newcomer. Photometry, spectroscopy, radar ranging, and the arcane art of light curve analysis become the languages of first contact. Each measurement is painstaking and provisional. A faint band in a spectrum can be the shadow of an unfamiliar mineral or the ghost of calibration error. Radar echoes can reveal a clue about rotation, but can be confused by irregular shapes. The entire enterprise becomes an exercise in humility, a shifting between conviction and doubt, between the hunger to declare certainty and the duty to withhold it. In the narrative that builds around an object like 3I Atlas, two interpretive pathways seem to diverge and then rejoin: the natural and the contrived. The natural explanation posits that 3I Atlas is simply a fragment born of natural processes. Tidal disruption of a planet. A collision ejected the shard into interstellar space. The shard survived, voyaged across cosmic deserts, and found its way into our backyard. The contrived explanation, which refuses the easy comfort of geological processes, asks if the anomalies might instead be signatures of intentional design, engineered structures, manufactured alloys, or patterns that betray a maker's hand. It is a tempting bifurcation because it mirrors a deeper human habit to decide between accident and intention when confronted with the inexplicable. Speculation about ancient, erased civilizations often spills into this second pathway. The imagination reaches for narratives of technological epochs that rose and then were ground down by the slow machinery of geology. The speculative documentary voice, the one that ponders deep time and possible secrets, is careful here. It does not leap to melodrama. Instead, it frames possibilities within the constraints of preservation and erosion. How likely is it that a technological artifact could outlast the turbulent forces of tectonics, weathering, and chemical dissolution? How might such an artifact be distributed through space? A plausible answer lies not in grand monuments, but in small, resilient forms: isotopic anomalies, non-natural element abundances, microstructures in ceramics, unusual alloys with specific isotopic signatures. If a civilization ever reached a technological peak and then disappeared, its fingerprints would likely be microbial, scattered, and faint. Yet sometimes the faintest fingerprints are the most telling. In imagining what 3I Atlas might reveal, it helps to think of the object as both an archive and a sieve. It archives the history of its origin system. It sieves possibilities by the biases of what endures. Radial waves die quickly. The ether is not a good long-term library. Structures dissolve under weather and subduction. But certain kinds of matter, refractory minerals, particular isotopic compositions, embedded microstructures, can outlast cataclysms. In the lithic grammar of planets, rocks can record episodes of atmospheric composition, flash heating from impacts, the presence of liquid water, or the chemical signatures of biological processes. The stranger the object's geology and chemistry compared to solar system norms, the more persuasive the claim that it came from an environment with a markedly different history. There is also a probabilistic scale to consider. Interstellar space is vast. The odds that a rock ejected from one planetary system will wander into a neighboring system are slim. But across the multitudes of stars in the galaxy and across the breadth of time, rare events become inevitable. If life and its technological offshoots are not unique, then rare events like interstellar exchange of matter could act as a form of cosmic postage, pieces of worlds traveling between stellar neighborhoods and, perhaps, between epochs. The presence of 3I Atlas is a physical instantiation of that postal service. It demands that hypotheses be scaled by both rarity and significance. A small probability multiplied by an enormous time span yields tangible expectation. The arrival of such a visitor forces a re-evaluation of epistemic comfort. Science prefers predictable systems, repeatable experiments, and controlled conditions. An interstellar rock offers none of these luxuries. It is a one-off, a single sample shot across the immensity. To extract robust inferences from it, methods must be both rigorous and imaginative. One reads its spectrum for clues to volatile components. One models its trajectory for clues to origin. One examines its small-scale structure for clues to fire, wind, or liquid action. Each technique yields data with wide margins and narrow certainties. Thus, the human response oscillates between feverish optimism and meticulous skepticism. Beneath the instrument and the analysis lies a more human set of responses. When a tangible piece of someplace else arrives, there is an immediate recalibration of identity. The sense of being alone in a vast, indifferent universe is splayed open into something less singular. There is also fear, the fear that the object might be a harbinger of phenomena that could disrupt human assumptions or even survival. But framed through deep time, fear reshapes into an ancient textured humility. Civilizations rise and fall. Landscapes remember nothing of the bluster of momentary species. The rock, silent and cold, becomes a teacher in that humility. It instructs by contrast. Here is endurance, here is amnesia. This encounter compels thought experiments about archaeology on a planetary and interstellar scale. Terrestrial archaeology concludes that preservation is capricious. Some materials endure, others disappear within centuries. Extrapolate that unpredictability across geological timescales, and the prospect of finding definitive artifacts of a vanished global civilization becomes unlikely. The more plausible traces are chemical and isotopic anomalies lodged in sediments, unusual distributions of elements, or perhaps nanoscopic structures that resist ordinary decay. An interstellar rock might be a better repository for such traces if its formative processes incorporated non-natural materials or unusual isotopic blends. It could, in principle, bear the echoes of technology that had a different longevity calculus, manufacturing choices that inadvertently favored preservation. Yet caution insists upon not rushing into narrative. The temptation to read purpose into patterns is ancient and human. Clouds are shaped into myths, constellations are stitched into stories. The scientific mind must interpret 3I Atlas through the language of probability and error analysis. But the human mind, when faced with the immense and the rare, naturally translates uncertainty into stories. That translation is not weakness, it is a cognitive tool that frames the questions science will then test. The story of an interstellar object thus becomes both an invitation to rigorous inquiry and a mirror of human longing for contact, for context, for evidence that the flame of organized intelligence has, somewhere, had enough time to make a mark. In this speculative documentary register, the most compelling image is not a definitive answer, but the shape of the pursuit. Instruments hum, data flows, models are iterated. Telescopes map the brightness variations. Laboratories extract spectral lines and compare them to databases compiled over decades. The object is catalogued, observed, until it slips back into the long interstellar night. And then it becomes part of a slow, scholarly conversation that will persist for years. Its bits of irregularity, those microaccelerations, those spectral quirks, are examined, re-examined, and reframed. Each paper published on the object is another stanza in a poem of caution and wonder. Ultimately, 3I Atlas functions as a provocation. It does not demand a single story be believed. It demands that multiple perspectives be entertained. It asks whether humanity will accept small, stubborn anomalies as windows into alien histories, or whether they will be written off as noise. It asks quietly whether the geological processes that obliterate evidence on Earth also make interstellar messengers uniquely valuable. It asks whether the discovery of such a visitor is a rare, clarifying event, or simply one more note in a vast, ongoing cosmic correspondence. In the end, the object is a reminder that the universe is both older and stranger than the neat narratives that make humans comfortable. It is a piece of another story that drifted into the margin of this one, and in doing so, it turned the page. The human impulse, upon reading that page, is to listen closely and to interpret carefully, to translate the faint chemical dialects into history, to weigh improbability against meaning, and to accept that sometimes the most profound lessons come from things that are small, silent, and utterly indifferent to human drama. The long view, the view that stretches across millions and billions of years, teaches a kind of stewardship of doubt, to hold rejection and wonder beside each other, to let curiosity lead while letting caution temper conclusions. 3I Atlas, as an interstellar visitor, was a prompt. It invited questions about origin and survivability, about the persistence of information, and about the possibility that other intelligences might have left traces not on grand monuments, but on subtle alterations of matter. It also forced a confrontation with Earth's own fragility and the limits of what time will leave behind. The object did not answer the grandest questions, but it offered an avenue through which they could be pursued. To look at it is to look back at oneself, a brief species on one small planet, trying to read the long handwriting of the cosmos, attempting to find meaning in the material remains of what may be the only means of interstellar memory available to them. Rocks that travel, that retain, that whisper across the deep, patient sweep of time. What happens when a thing that was born under another sky, a piece of ice and rock that remembers temperatures, pressures, and chemistry from a star that is not the sun, strikes the skin of this planet? That single question compresses the scale of deep time into an instant of violence and consequence. It asks how a moment can rewrite a chapter of Earth's history, how an object that has wandered the interstellar dark for perhaps millions of years can become, in a flash, part of the geological memory of a world that has itself kept secrets for eons. 3I Atlas in the portrait already drawn by instruments is an object that did not belong to the solar system. It carried the brittle signatures of absolute cold, volatile ices, trapped gases, an exterior pocked by microcraters and radiation scars accrued in the slow, indifferent exposure of interstellar space. It could have been vast enough to be called cathedral-sized, a monolith in the human scale, small in the cosmic sense, but large enough to alter weather for a season, to carve rock, to start fires, and to project ejecta high above the atmosphere. It could equally have been more fragile, a loosely bound aggregate of ice and dust that would disintegrate as it met pressure and heat. The truth of its effect on Earth depends on that anatomy, the balance of density to porosity, of volatile to refractory material, of internal strength to centrifugal fractures. The journey from the dark begins with approach. As the object slips from interstellar oblivion into the sun's gravitational embrace, it accelerates. The relative speed is not measured in leisurely orbital days, but in tens of kilometers per second, velocities that turn mass into instantaneous energy. The atmosphere is a thin but lethal gate. To human instruments, the last moments of 3I Atlas's approach would be read as a brightening streak, an arc of light that registers as heat, ionization, and mechanical stress. The topmost layers of the object begin to sublime and ablate. Volatile ices turn to vapor, releasing jets and potentially changing orientation. If the object is porous and icy, this devolatilization acts like a pressure valve. Fractures open, pieces fall off, and a once coherent body may break into a train of smaller projectiles. If it is compact, metal-rich, or icy but robustly welded by impact sintering, it may resist breakup and carry most of its mass to lower altitudes, and, if large enough, to impact. There are different scales to the consequences, each with its own choreography of destruction and record. On the smaller end, an atmospheric airburst, a disintegration above ground, can concentrate energy into a pressure wave that flattens forests and shatters windows across a wide radius. The 20th century offers precedents, explosions in thin air that cause widespread damage without forming a crater leaf, a very particular signature. On the larger end, a solid impactor that punches through the atmosphere and meets the ground or ocean produces a crater, an ejecta plume, seismic waves recorded circumnavigating the planet, and an atmospheric veil of dust and aerosols. Whether the event is regionally devastating or globally disruptive hinges on size and the nature of the target, land or ocean. If 3I Atlas struck solid ground, the immediate scene would be of concentrated violence. Kinetic energy converts in a threshold, shocking instant. Rock vaporizes at the point of contact, molten material is thrown high, and a transient cavity collapses to leave a circular depression. The local environment becomes a furnace. Thermal radiation ignites fuels over a large area. Shockwaves radiate outward, collapsing structures, toppling trees, crushing the landscape into a new topography. Nearby ecosystems would be erased, and ash and aerosols would be lofted into the stratosphere where they could ride global winds. The footprint of such an impact extends far beyond the crater itself. Harvests fail on scales measured in months. Climatic perturbations last for years, and the human sensory world, the color of sky at sunset, the chill of sunlight, is altered for a generation. If the impact occurs in oceanic waters, the dynamics shift, but the potential for global consequence often increases. An oceanic strike injects colossal volumes of water, steam, and dissolved salts into the atmosphere. It can launch tsunamis with wavelengths that cross basins and degrade coastal civilizations far from the point of contact. Steam and volatiles entering the stratosphere act as climate agents. Water vapor can increase greenhouse forcing in subtle ways, while salt and soot can combine to alter radiative balances. For an icy interstellar object rich in volatiles, the ocean impact is a complex mixing event. Sublimated ices and entrained sediments mingle with seawater, creating plumes that travel as dust and droplet-laden currents across hemispheres. Beyond the immediate physics lies the climate response. A veil of dust and aerosols can reduce insulation and initiate a planetary cooling, an impact winter. Sulfate-rich rocks, when vaporized, seed atmospheric chemistry that produces sunlight-blocking aerosols, soot from ignition of. Biomass amplifies this effect. Photosynthesis falters, food chains contract, and ecosystems that depend on stable seasonal productivity unravel. The severity of biospheric disruptions scales with the magnitude of atmospheric loading. For humanity, the consequences ripple through infrastructure, supply chains, strain, agriculture falters. Social systems face stresses that testing institutions often cannot bear. For geological time, these perturbations register as brief but sharp anomalies, sudden declines in diversity among the microfossils, a collapse of pollen records, shifts in carbon isotopic compositions. The deeper significance of such a collision, and the element that most demands the attention of a speculative documentary voice, is its capacity to enshrine or to obliterate information. An interstellar visitor is itself an archive. Its interior, shielded by ice and mineral, may host complex organics, isotopic ratios that betray formation temperatures, or inclusions that formed under chemical conditions foreign to the solar system. Impact is a paradoxical process for that archive. On one hand, it is destructive, vaporizing, and melting. On the other hand, it forges newly resilient repositories. Impact glass, rapidly quenched silica that formed under the heat and then froze, can encapsulate microscopic slivers of the original material. Spherules, glassy beads produced in the hot plume, rain out and become part of the sedimentary record. These microarchives can preserve the fingerprints of a foreign chemistry inside Earth's own strata. The geological signature left by such an event is distinctive, and it is precisely these signatures that future geologists, looking back across deep time, might read. A layer of glassy spherules, an anomaly in the abundance of certain refractory elements, shocked quartz grains with diagnostic planar deformation features, a spike in impact-related isotopes. Together they compose an event layer that can be mapped across continents. If the impactor carried unusual isotopic ratios of oxygen, carbon, nitrogen, noble gases, those ratios could be identified against the background of Earth's chemistry. If the object deposited exotic minerals or even metallic phases not commonly produced in terrestrial geology, those phases would stand out as whispers of an origin beyond the sun. There is also the question of preservation. Deep time is a relentless editor. Plate tectonics recycles crust, oceans bury and exhume sediments, weathering reduces sculpted forms to chemistry. A dramatic impact produces an unmistakable but not necessarily permanent mark. Large craters can survive geological turnover for tens to hundreds of millions of years, yet even craters are flattened and obscured by sedimentation and erosion. The chemical signatures survive longer in many cases, lodged in sediments and in the chemical memory of ocean basins. Thus, the collision of 3I Last would imprint both a geomorphic scar and a chemical stanza in Earth's hymn, one that would be read by those who know the decoding keys, stratigraphy, isotopes, trace minerals. There is another, more haunting possibility tied to the nature of the visitor. If 3I Last carried complex organic molecules, stubborn chains or pockets of solvent-laden chemistry, the violence of impact might liberate, alter, or destroy them. High pressures and temperatures can synthesize new compounds. They can also vaporize pre-existing assemblages. Some fraction of pre-impact organics could be trapped in impact glass, shielded from the full fury of the event. In that way, an impact becomes an act of preservation for certain classes of matter, even as it is the ultimate act of obliteration at macroscopic scales. The record of pre-terrestrial organics could therefore exist embedded in the very fallout that, at larger scales, spelled destruction. Because 3I Atlas is interstellar, its isotopic vocabulary may speak about formation conditions impossible to reproduce in the solar system. Ratios of, for instance, rare isotopes could betray a nucleosynthetic ancestry or point to chemical pathways fostered by different temperature regimes. Those subtle signatures would be precious to human scientists, not as narrative proof of alien intelligence, but as empirical evidence of chemistry beyond the local neighborhood, a specimen that expands the catalog of how matter arranges itself in planetary environments. The collision would thus be a clarifying act, violent, yes, but also revelatory, if the surviving fragments are examined with the patient ingenuity of geochemists. Yet the human scale of consequence must be acknowledged. Even an object modest in cosmic terms can be devastating in civilizational terms. Local economies vanish, supply routes collapse, the optics of governance are tested. The social memory of the event might be preserved as myth, ritual, or record. But the archaeological trace of a 21st century civilization could be faint within a few 100,000 years. Paradoxically, the very event that threatens immediate continuity on impact also deposits durable material that may outlast. The fragile trinkets of modernity, radio transmissions are ephemeral, plastics fragment and oxidize, skylines subside, but a layer of global fallout, a unique isotopic marker, and shards of impact glass containing exotic matter could remain as the clearest testament that once species looked up and catalogued the skies. The psychological reverberations of a cosmic collision are part of the story too. Humans interpret catastrophe through narrative frames: punishment, test, warning, or awakening. The image of a foreign rock striking Earth presses a series of existential questions into the foreground. What does it mean to be vulnerable to events that originate outside human intention or local geological cycles? How does a species that measures time in decades reconcile itself to processes that unfold in millennia? There is both dread and a strange consolation in the recognition that much of what a civilization counts as permanence is not. Immutable, the planet can be reshaped by forces indifferent to moral ordering. From a documentary vantage, the fascination is not merely with the spectacle, but with the interplay between fragility and endurance. The impact is an agent of both erasure and inscription. It is a punctuation mark in the sedimentary record, a thickened page where chemistry is reordered and memory is both created and smudged. It forces a recalculation of the probabilities by which matter moves between stars and how planets inherit that matter. It serves as a reminder that interstellar exchange, once conceived of as a curious side channel, can have direct terrestrial consequences. Finally, the collision is also a narrative hinge. In one telling, it is a calamity, a rupture in the continuity of life. In another, it is an opportunity for knowledge, an unplanned sample of a different planetary system arriving in Earth's own laboratory. The dialectic between these interpretations, disaster and archive, is what makes the event compelling to the speculative mind. For deep time keeps both registers alive. Deserts once teeming with life become repositories of evidence. Cataclysms that killed off species also created niches that spawn new forms. The geology of Earth is written in cycles of loss and emergence, and an interstellar impact would be another line in that script. In the end, what might happen if 3i last struck Earth resists a single, crisp answer? The physics is well understood, the consequences can be modeled. Yet the real story is the web of cascading effects, mechanical, chemical, ecological, social, that unfold across scales of time. The collision would be a violent conversation between two histories, the cold, patient narrative of an object forged elsewhere, and the hot, evolving biography of a living planet. It would be an event that both removes and records, a violent act that writes itself into the archives of deep time. To contemplate that possibility is to confront, in miniature, the larger truth of planetary existence. Permanence is an illusion. Endurance is selective, and meaning often hides in the fragile seams where foreign matter becomes part of a world's own story. What happens when a thing that has been wandering for millions of years between the stars, a cold fragment carrying exotic chemistry and the memory of alien suns, finally meets the dense, noisy skin of a living planet? The question compresses epochs into an instant, the patient arithmetic of cosmic travel slammed against the brute arithmetic of impact. It is a question about force, about information, and about the strange double role of violent acts as both erasers and archives. Approach is a choreography of inevitability. An interstellar object like 3i Atlas arrives not as a slow visitor, but as a vector of kinetic intent. Its speed, measured against the heliocentric frame, is not the leisurely tens of meters per second of terrestrial motion, but tens to hundreds of kilometers per second velocities that render mass into vast kinetic budgets. The atmosphere becomes, at the threshold, an exquisitely efficient brake, a thin, tenuous envelope that, over a few tens of kilometers, can turn a piece of stone into light and pressure. The physics of entry reads like a series of escalating tests. At high altitude, the first contact is thermal. Gas molecules that before occupied no meaning for the rock suddenly slam into it at tens of thousands of times the energies they usually carry. The leading surface is stripped by ablation. Volatiles trapped in pores and in ice sublimate, erupting in jets that can torque the body, change its orientation, and in porous aggregates open fissures. Radioactive scars and cosmic ray tracks that were accrued over millions of years do nothing to soften the new strain. If the object is a loosely bound conglomerate of ice and dust, it will behave like a house of cards under wind. Pieces will peel away and burn individually, creating an incandescent train across the sky. If, however, the object is a compact block of refractory material or an alloy unusually resistant to thermal stress, most of its mass may survive the plunge and deliver its full budget of kinetic energy to the lower atmosphere and the surface beneath. To make the scale of that energy comprehensible requires numbers, and those numbers are arresting. A solid body the size of a cathedral, a notional 100-meter scale object with a mass on the order of 10·9 kilograms, striking at 50 kilometers per second, carries kinetic energy measured in 10·118 joules. that is hundreds of megatons of TNT, thousands of times larger than the most destructive human explosive devices, and comparable in regional destructive power to the largest natural events in recent geological memory. Smaller objects at similar speeds still carry energies that dwarf the human scale. A 20-meter fragment can deliver megaton range effects. The decisive factor is velocity squared. Doubling speed quadruples the energy delivered. Interstellar velocities, then, are a force multiplier. Deceleration in the atmosphere is a lesson in brutal gradients. Forces on materials and on entrained gases translate into g-forces measured in the hundreds or thousands for fragments that survive deep penetration. The outer layers of rock are sheared off by aerodynamic stress. Shock heating transforms minerals. Volatile inclusions flash to gas and expand with furious impatience. This is not a slow erosion, but an explosive renegotiation of matter. The result diverges into familiar archetypes: an airburst high in the atmosphere, a ground impact that excavates a crater, or an ocean strike that sends patterned waves across basins. The airburst scenario is deceptively destructive. When a body unloads its energy several kilometers above the surface, the resulting pressure wave can flatten trees and buildings over vast tracts without ever leaving a classical crater. Thin air that is suddenly overpressured becomes a hammer that travels at supersonic speeds across landscapes, toppling everything in its path. Witnessed in the geological record, such an event leaves a particular signature: shocked grains, microscopic melting, and a field of flattened vegetation where the imprint resists simple erosion, but the lack of a crater can make attribution ambiguous unless coupled with global chemical anomalies. If the object survives to strike ground, the theater of destruction becomes more localized in morphology but broader in consequence. Kinetic energy at the instant of contact converts into heat and pressure so intense that rock vaporizes, a fireball expands, and molten ejecta is hurled high into the sky. A transient cavity forms and collapses, leaving behind a circular scar stamped into the crust. Around that scar, rock is shocked and altered. Quartz grains show planar deformation features that could be read by future geologists as incontrovertible evidence of an impact. Melt sheets and breccias capture the violence in their fabric. The local biosphere is obliterated. The atmosphere receives a pulse of dust, soot, and vaporized material that circulates on global scales. The ocean strike outcome carries its own amplified consequences. When a large mass meets water, the immediate thermal and mechanical exchange injects steam and droplets into the upper atmosphere. Tsunamis with wavelengths measured in hundreds of kilometers radiate outward, striking distant coasts with fraudulent suddenness. Water acts as an amplifier and a medium. Salt and dissolved compounds hitch a ride into the stratosphere, affecting radiative and chemical balances. For icy interstellar bodies loaded with volatiles, an oceanic impact is a complex mixing event in which alien ices, dissolved gases, and particulate matter are scattered into seawater and air alike, producing fallout that can register in sediments far from the point of contact. Beyond mechanical devastation, the climatic feedbacks would turn a local catastrophe into a planetary crisis. The lofted cloud of dust and aerosols, amplified by combustion products from burning vegetation and by sulfur species released, when sulfur-rich target rocks are vaporized, can reduce surface insulation for months to years. This so-called impact winter is a compression of seasonal cycles. Photosynthetic productivity collapses, temperature gradients shift, and ecosystems that depend on tight seasonal cues fall out of sync. Agricultural systems reliant on predictable climate would experience crop failures on scales that quickly translate into social crisis. In the geological ledger, such episodes correlate with spikes in extinction rates, abrupt shifts in carbon isotope ratios, and disruptions in pollen assemblages. A single event can, therefore, leave an imprint both in mortality and in the chemistry of sediments that persists for millions of years. And here's the paradox that deep time poses. Violent erasure can be paired with potent inscription. The heat and pressure of impact also create the very materials that serve as archives. Rapid quenching of molten silicates produces impact glass, tiny beads and larger melt sheets that can encapsulate fragments of the original body, preserve complex organics in a shielded microenvironment, and lock in isotopic ratios against later chemical reequilibration. Spherules formed from condensed vapor rain out across the planet, forming a layer of glassy fallout that, if preserved, becomes a globally correlatable event horizon in the stratigraphic record. Shocked minerals carry in their deformation patterns the fingerprint of extreme pressure. Certain isotopic anomalies of oxygen, nitrogen, or noble gases may be preserved in these matrices and thus offer a direct measurable line back to the chemistry of the interstellar origin. These preserved signatures are precious because they can be unusually diagnostic. An interstellar visitor may carry isotope ratios that differ subtly but detectably from solar system norms, either because of formation at a different temperature regime or because of nucleosynthetic histories unique to its birth environment. Exotic refractory phases or metallic alloys with unusual trace element signatures could stand out like dialects in a language otherwise uniform across the crust. Even if macroscopic artifacts of a hypothetical technology are utterly destroyed, the micro and nanoscale chemical residues can survive. Impact glass is, in a sense, a micro-archive forged in the furnace of catastrophe. There is, inevitably, a question about biology. Could such an interstellar fragment seed life, alter it, or sterilize it? The answers are bound by probabilities and by chemistry. High-energy impact tends to be sterilizing at the point of contact. Most complex molecules are broken or transformed. Yet a small fraction of pre-existing organics can be entrapped within glass, shielded from both ultraviolet cataclysm and chemical oxidation, and thus survive in a modified form. In theory, material delivered intact could introduce novel chemical species to local environments, providing unexpected substrates for chemistry. The more dramatic claim that interstellar objects are efficient agents of panspermia requires delicate balances, survival of complex molecules over cosmic timescales, survival of those molecules through entry and impact, and then a favorable environment on the receiving planet. It is not impossible, only improbable, that across the vastness of time and the multitudes of stars, improbable events accumulate into plausibility. Preservation in the stratigraphic record is itself a negotiation with time. Plate tectonics recycles crust, oceans bury and exhume sediment, weathering softens and buries sharp geomorphology. A crater's visibility fades, topography is dressed over with subsequent deposits, and glassy spherules can be redistributed or dissolved. But chemical anomalies and resistant mineral phases can linger far longer than landscapes. A distinct layer, rich in platinum group elements, for example, can persist and be recognized as anomalous tens or hundreds of millions of years later. The same is true for a unique isotopic fingerprint or a horizon of shocked minerals. Thus a violent encounter can serrate the stratigraphy with a slice that, if sought, can be read even by eyes separated by epochs. There is also an epistemic drama in the human response to such an event. Instruments and networks tuned to the sky would register the approach and the impact, optics catching the luminous entry, seismometers remarking the ground motion, satellites tracking the plume. The scientific process would pivot from observation to reconstruction, modeling trajectories, sampling fallout, analyzing glass, and drilling sedimentary sequences in search of a global marker. In time, the event would be stitched into the scientific literature as a chapter in planetary history, causal chains proposed, refuted, refined. That process is slow relative to shock and disaster, but durable relative to hysteria. The long view is not indifferent, but patient. It uses careful stratigraphic and geochemical work to turn a violent singularity into a reproducible data point. Finally, the collision embodies a philosophical symmetry that is central to the speculative documentary voice. The interstellar fragment is both messenger and judge. It arrives bearing the chemistry of a different world, and in doing so, it may deposit something that deepens human knowledge. Yet the same collision can destroy, reconfigure, and erase the ephemeral marks of contemporary civilization. There is a bitter irony here. The most durable traces of a technological species may not be its monuments or digital archives, but a layer of fallout in a sedimentary basin, a globally distributed chemical bookmark that, in a few 100,000 years, constitutes the clearest testimony of human presence. To imagine such a strike is, therefore, to hold two images at once. One is of obliteration. Forests flattened by a pressure wave, coasts redrawn by towering waves, skies dimmed by an aerosol veil. The other is of preservation, glassy beads raining down, isotopic anomalies embedded in organic-rich sediments, a unique layer that future geologists would read like a line break. It is the paradox of impact, to wind up the clock by destroying some chapters while writing a new, stubborn chapter into the rock record. For a species conscious of its own brevity, the collision is an existential tutor. It teaches that permanence is a fragile illusion, and that continuity depends on contingencies. It also teaches that knowledge often arrives wrapped in calamity. An object that traversed a galaxy for millions of years can, in minutes, become both a cause of suffering and a source of new understanding. That duality, Catastrophe and archive, erasure and inscription is the heart of what happens when something born under another sky meets this one. The planet bears the scars and the records, and deep time, patient and capacious, keeps the ledger where future readers, if there are readers at all, might one day translate the chemistry of a stone into the story of an encounter. What would the collision zone feel like, sound like, look like? And what would it leave behind when a messenger from another star met the fragile skin of this world? The question is not merely one of spectacle, it is a hinge between scales. It asks how the slow, indifferent history of interstellar travel translates into a single, violent sentence written across atmosphere, lithosphere, biosphere, and human institutions. In imagining that sentence, one must move through layers of physics, chemistry, and social consequence, and listen for the smaller, quieter things that survive among the roar. Modelers begin by reducing the unknown to parameters: mass, density, velocity, angle of approach, and target, land or ocean. Each axis alters the choreography of destruction. An object the size of a cathedral, depending on internal cohesion and speed, can behave like a bright meteor that streaks and disperses, or like a compact bullet that punches through the air and deposits its energy on the ground. The numbers are stark because kinetic energy scales with the square of velocity. A body arriving at tens of kilometers per second carries a budget of violence that makes ordinary disasters seem domestic. Yet the geometry matters too. A shallow angle disperses energy higher in the atmosphere, producing an airburst that levels forests and cities without leaving a classic crater. A steep, compact strike concentrates energy into rock, vapor, and molten glass and carves a new indentation into the crust. The approach itself is already a small drama. At high altitude, the first chemical conversations happen. Molecules of air collide with the front of the rock at hypersonic speeds, compressing and heating into a luminous sheath. Ices that have remained solid for millions of years flinch into vapor. Trapped gases erupt in jets that twist the body. When porosity dominates, the object becomes a cathedral opened like an accordion by pressure. Chunks peel away and glow independently. When coherence dominates, the body retains its dignity until the instant of contact, and then that dignity is transformed into singular heat. If the object breaks apart in the upper atmosphere, an airburst, the violence is diffuse but still terrible. The airburst is a pressure phenomenon. Energy released at altitude propagates as a supersonic overpressure front, a moving hurricane of compression and rarefaction. Buildings experience a sudden, uncustomary load that they were never designed to withstand. Glass shatters into a glittering rain. Walls buckle, and the sound is not a roar, but a vast, sustained pushing of the air itself. Trees are snapped like twigs. The historical analogues are instructive. The Tunguska event of 1908 felled millions of trees across a forested basin without a crater. An airburst the size of a cathedral-scale interstellar visitor would do this over a continental-scale swath of landscape. The nearby horizon would become a furnace. Distant horizons would still register the pressure change. If, however, the body survives to reach the ground, the scene rearranges into the classical theater of impact. Kinetic energy compresses at a rate that melts rock into vapor. A fireball blooms and then collapses into a transient cavity. Plume dynamics then take over. Molten and vaporized target rock, mixed with fragments of the impactor, are lofted into ballistic trajectories that fall out as teardrops of glass and as spherules. The new crater, its size and rim morphology determined by impactor size and target lithology, becomes an immediate obliteration of ecosystems within its radius. The blast does not respect borders or property lines. It rewrites topography and leaves behind surfaces that will for a long time be unfamiliar to any species that had lived there before. An ocean strike writes a different signature into the world. Water expands and steam explodes, injecting enormous volumes of vapor and particulate matter into the atmosphere. Tsunamis are generated with wavelengths that travel across basins, whispering and then howling into distant shorelines that may have no direct visual relationship to the point of impact. Salt and dissolved ions hitch a ride into high altitudes, modulating radiative balances in ways that are subtle at first and then catastrophic. For an object carrying volatiles, sublimated ices, and trapped gases, the ocean interaction becomes a complex chemical mixing event. Alien ices encounter terrestrial salt and organics. Reaction kinetics occur at high temperature and pressure, producing species that did not exist in the local seawater a few hours prior. Beyond the immediate physics, the atmosphere becomes a medium of global consequence. Vaporized rock and soot from ignited biomass form a veil that can reduce the sunlight reaching the surface, an impact winter. The degree and duration of this dimming depend on the quantity and composition of lofted material. Sulfate aerosols are particularly effective at scattering sunlight, and if the impact happens in a sulfur-rich target, climate forcing can intensify. Soot amplifies the darkness. Submicron dust particles linger in the stratosphere and decorrelate. Seasonal cycles. Photosynthesis, the slow business on which planetary ecosystems hinge, is shortened or disrupted. Food chains constrict. Primary productivity collapses. The errors of seasonal timing ripple out into mass mortality events. For human systems dependent on calibrated agriculture and interconnected logistics, crop failure in several successive seasons can translate into political stress, resource hoarding, migration, and social fragmentation. This is the chart of immediate calamity. Equally important, and less intuitively violent, is what the event writes into the rocks. The paradox of impact is that destruction produces durable archives. When molten silicate sprays into the air and then cools rapidly, it forms glass, tiny beads and larger sheets that can preserve chemistry and microstructures against subsequent alteration. Spherules rain out across continents, producing a layer within sediments that future geologists could use as an event marker. Shock coding and planar deformation features in quartz grains are microscopic fossilizations of pressure. They are, in the lexicon of geology, incontrovertible signatures of extraordinary force. If the impactor carries isotopic ratios different from those typical of the solar system, subtle, measurable departures in oxygen, nitrogen, or noble gases, those ratios can be locked into fallout materials and lodged in oceanic sediments for millions of years. There is a further, smaller-scale drama in chemistry, organics, and complex molecules. High-energy shock and heat will destroy much of any pre-existing macromolecular inventory carried by the visitor. Yet some molecules can be trapped within rapidly quenched glass, shielded from ultraviolet photolysis and later oxidative weathering. In this way, the impact is both a micro-scale executioner and a curatorial force. It burns the husks but entombs fragments. The result is that the geological record, that patient, sedimented ledger, can contain exquisitely specific clues about the origin chemistry of the object, even while the surface whirled. Reels from its immediate effects. Simulations help render this into approximate landscapes of possibility. As the visitor is loosely aggregated ice and dust with low density, the most likely outcome is staged breakup in the upper atmosphere and a wide field of energetic airbursts, intense, localized destruction without a single crater but with significant atmospheric loading. If the visitor is dense and compact, a rock or metal-rich body, it will penetrate lower and produce a crater, melt target rocks, and generate a global fallout layer. For an event with a kinetic energy in the range of tens to hundreds of megatons, the region of total ecological devastation might span thousands of square kilometers, with atmospheric and climatic consequences reaching hemispheric scales. For energies orders of magnitude higher, the consequences become planetary, sustained global cooling, major disruptions to oceanic circulation, and an extinction-level reordering of biospheric communities. Those extreme cases are not offhand probable for a cathedral-sized body, but the parameter space of interstellar visitors is wide, and among that width lie both the measured and the unimaginable. There is a social choreography after the physical: observation, triage, adaptation. Instruments capture the luminous entry and map the plume. Seismology records the heartbeat of the ground. Satellites sample the particulates lofted into the stratosphere. Emergency response shifts into triage of human need: shelter, food, water, medical care. On longer scales, societies recast priorities. Some energies devoted to repair and recovery, some to preservation of knowledge, some to recalibration of risk perception. Myths and rituals often follow calamity. The human mind translates trauma into story. In the stratigraphic sense, the cultural memory often decays faster than the geochemical anomaly. Radio transmissions scramble and fade, plastics fragment and oxidize, monuments collapse. Yet the fallout layer and the isotopic signatures persist. Paradoxically, the violent event that threatens immediate continuity often writes the most persistent testimony of that. Continuity into the stone record. This paradox opens a philosophical register. Catastrophe can be archival. Erasure at the level of cities is paired with inscription at the level of molecules. The same blast that flattens trees can produce spherules that, millions of years hence, speak to assemblages of isotopes foreign to the solar system. Thus, an interstellar collision functions both as destructor and as archivist, and the record tends to privilege certain kinds of persistence refractory minerals, glass, isotopic anomalies, while betraying delicate, ephemeral artifacts. The question of preservation reaches into the question of memory across deep time. Plate tectonics recycles crust, sedimentation buries and exhumation reveals, chemical weathering reshapes with slow patience. Craters are filled, rims are worn down, yet a global fallout horizon, a discrete layer composed of condensed vapor and splashed glass, can be correlative across continents and thus serve as an unmistakable stratigraphic marker. In that way, a single impact can be more legible 100 million years hence than sprawling human cities are today. The irony is acute. The things cultures consider most durable, towers, monuments, digital networks, are surprisingly ephemeral by geological standards. The stuff that survives is unromantic and small, a kind of sedimentary punctuation that a future geologist might read as proof of a dramatic encounter. On biospheric timescales, the event is a pivot. Species that suffer immediate mortality may make way for others. Ecological niches reconfigure, chemical cycles slow or accelerate. In some paleontological precedents, mass removals were followed by bursts of innovation and radiation among surviving clades. Cataclysm is a harsh sculptor. It can end chapters and open others. The idea is not consolatory in any simple sense, but it insists that planetary histories are not linear narratives of decline or progress. They are sequences of punctuated reorganization. Finally, the collision zone is an ethical lesson about contingency. The planet has a catalogue of rare but consequential events. Human societies can be robust, adaptive, and resilient, and yet they remain vulnerable to the arithmetic of chance. Preparation is a social technology, better observation networks, evacuation strategies, diversified food systems, and governance that can act swiftly and equitably. Scientific curiosity is another kind of preparation, knowing what to sample, how to preserve fallout, how to recognize isotopic anomalies as potential messages from elsewhere. The same scientific tools that parse the chemistry of a spheroid also provide the models that translate an incoming trajectory into coastal warnings and airburst maps. The operative image, then, is of a conversation between histories. The interstellar object brings a slow biography encoded in its mineralogy and isotopes. Impact translates that biography into a local sentence of fire, pressure, and dust. The planet answers with its climate, its lithosphere, its seas, and its living systems. What remains? Geomorphic scars, blast beads and clay, altered isotopic ratios, becomes part of the ledger of deep time. For the species that experience the event, there is shock and mourning. For the species that read the layers a million years later, there is a crisp stratigraphic word here, something foreign touched Earth. To describe the collision zone is, therefore, to describe a multi-layered palimpsest, immediate, terrifying, sensory, chemical, and microstructural, and preserved, social and mythic and vulnerable. Each layer refracts the meaning of the encounter differently. In the quiet hours after the dust begins to settle, when luminescence dwindles and the soundscape returns to a new normal, the planet will begin the slow work of writing the event into stone. That is the enduring fact. Violence and memory are not opposites on this scale. They are companions. The fire that clings the landscape also casts tiny beads of blast that will, in remote future, be read as evidence of a visitor that came from another sky. What if sunlight were stolen for a season, not by clouds of weather that come and go, but by a thin, persistent veil that the planet itself had not seen for millennia? The thought frames the event with an almost surgical clarity. An impact does not merely break things, it borrows the sky. It transforms radiative balance into a ledger of loss, and that ledger writes itself in temperatures, in harvests, in the slow breathing of oceans and ice. When an interstellar visitor strikes a living world, the most far-reaching consequence is often not the crater, not the local blast, but the climate's response, an impact winter, a collision season that can rearrange biospheres and human societies alike. The mechanism is straightforward and merciless in its simplicity. At the instant of contact, an enormous amount of kinetic energy is converted to heat, pressure, and motion. Rock vaporizes, target materials explode into fine particulates, sulfur-bearing minerals are vaporized into gaseous species, vegetation ignites, and cities, clusters of fuel and infrastructure, become sources of soot. Tiny particles, from pulverized rock to condensed silicate droplets to combustion-produced black carbon, are lofted high into the atmosphere. If the event is energetic enough, the plume punches through the weather layer into the stratosphere, where winds are slow and mixing is weak. There, particulate matter and aerosols can reside for months, sometimes years. In that position, they become efficient agents of radiative forcing, scattering and absorbing sunlight before it reaches the surface, cooling the world below while painting sunsets with a peculiar intensity. Not all particles are equal. The climate effect depends on size, composition, and altitude. Fine sulfate aerosols, produced when vaporized sulfur oxidizes, are efficient reflectors of solar radiation. Soot, by contrast, is dark and absorbs sunlight, heating the stratosphere even while shading the surface, and it can catalyze complex chemical reactions that erode protective layers like ozone. Coarse dust falls out faster. It contributes locally to reduced light but is less persistent. The interplay among these constituents determines how deep and how long the planet's sunlit face will be dimmed. A rocky impact onto sulfur-rich carbonates will inject a different atmospheric cocktail than an icy body that vaporizes with salts and volatiles. The planetary consequences are therefore a function of both the impactor's chemistry and the target geology. If the point of contact is ocean rather than land, the immediate human picture becomes exponentially grim in other ways. Water has a peculiar generosity in making waves. An oceanic impact displaces gargantuan volumes of water in a matter of seconds, launching tsunamis whose wavelengths can span entire ocean basins. Coastlines half a world away become front lines in a few hours. Cities built for centuries along those margins find themselves exposed to forces that do not recognize borders or the thin line between human order and natural geometry. But ocean impacts are double-edged. While they send waves across coasts, they loft enormous plumes of steam and salt into the air. Salt can react in the stratosphere in ways that alter cloud properties. Steam can transiently increase greenhouse forcing, and dissolved materials can ferry alien chemistries into oceanic currents. The ocean itself becomes both transmitter and archive of the collision. The immediate climatic response, the impact winter, plays out over a hierarchy of timescales. Within days to weeks, diffuse dust and soot dim sunlight. Surface temperatures fall, sometimes precipitously, depending on the magnitude of the aerosol loading. If the event ejects enough dark material into sunlight-bearing layers, photosynthetically active radiation is curtailed, and the slow engines of life, plants, phytoplankton, begin to sputter. Within months, the seasonal cycles that plants and animals depend on begin to unravel. Crops that rely on predictable day lengths and cumulative warmth may fail to mature. Migratory patterns linked to seasonal signals lose their cues. The first harvest after the event is a brittle test of resilience. If it fails over large regions, subsistence collapses, ripple into markets, trade, logistics, and governance. But the story does not stop at agricultural upset. The biosphere is a web of dependencies. Reduced primary productivity at the base of food chains diminishes the energy available to herbivores and, subsequently, predators. In oceans, phytoplankton flourishes or fails with the light. A prolonged dimming reduces surface productivity, which starves entire trophic cascades and can alter carbon sequestration dynamics. Ironically, an impact that kills off large coastal ecosystems can reduce short-term biological uptake of carbon even as fires and decompositions release carbon dioxide. Thus, the carbon cycle experiences a fast jolt of perturbations, an initial cooling phase, followed possibly by transient increases in greenhouse gases that feed back into climate on decadal scales. Feedbacks can deepen the crisis. The initial cooling can expand sea ice at higher latitudes. Increased albedo from spreading ice reflects more sunlight than before, amplifying cooling in a classic positive feedback loop. Ocean circulation may slow, as surface waters change density with cooling and altered salinity patterns, for instance. From enormous contributions of meltwater, such changes can cause regional climates to diverge dramatically from the global mean. Europe, reliant on heat distribution from ocean currents, might experience harsher winters for years. Monsoon systems in the tropics can weaken, starving regions reliant on predictable wet seasons. Weather regimes cascade into a new normal that took an instant to begin and perhaps decades to settle. Chemical consequences are equally insidious. Vaporized sulfur becomes sulfur dioxide and then sulfate aerosols, the stalwarts of prolonged radiative cooling after a big impact. Nitrogen compounds, forged in high-temperature shock and combustion, enter a chemistry that produces nitric oxides capable of depleting ozone. Ozone depletion allows for spikes in biologically damaging ultraviolet radiation once the sun returns to its prior intensity, creating a twofold injury: surface cooling in the near term and enhanced UV exposure in the aftermath. Acid rain results from oxidized sulfur and nitrogen species, which can acidify soils and freshwater systems, further stressing vegetation and aquatic life. In short, the atmosphere becomes a chemical theater where radiative and reactive actors recompose the rules of habitability. Human societies respond on a convoluted spectrum. Some institutions draw quickly on reserves, others buckle under the logistical strain. Food, the basic substrate of social stability, becomes rationed, traded, smuggled, hoarded. Migration follows the lines of water and warmth. Entire populations might press toward more benign climates or arable enclaves. Governance systems are tested by the demands of distribution, security, and public health. Cultural life, stories, rituals, music, often recalibrates around the event, encoding it into collective memory as myth or cautionary tale. In a documentary register, these responses are not recounted through the arc of a hero or a leader, but through patterns. Supply chains rewired, agricultural calendars redrawn, neural networks of trade and aid re-established. The social landscape alters as palpably as the physical one, yet this collapse also reframes the long view. The planet's geological memory will carry distinct signatures of the collision, layers of fine spherules and glass, spikes in sulfate deposition visible in ice cores, anomalous soot horizons in marine sediments, isotopic perturbations in carbonate records. These are the durable archives that paleoclimatologists and geochemists recognize as the handprints of abrupt events. The narrative is paradoxical. The things humans see as fragile, crops, cities, ephemeral digital architectures, can be swept away, but the collision writes an economy of persistence in minerals and isotopes. A thin, dark veil across the sky becomes, for future readers of deep time, a crisp horizon line. The amplitude of the impact winter depends on scale. Volcanic eruptions such as Mount Tambora in 1815 produced a year without a summer, with demonstrable agricultural and social sufferings, but the scale of a large extraterrestrial impact can exceed volcanic episodes by orders of magnitude. The Chicxulub impact, which coincides with the end Cretaceous mass extinction, shows what is possible at planetary scales. Sunlight dimmed, ecosystems overturned, and recovery stretched across hundreds of thousands of years. Smaller events, nonetheless, can produce century-scale perturbations that manifest as political collapses, migrations, and cultural resets within human timescales. Importantly, magnitude matters less than distribution. A well-placed ocean impact can generate tsunamis and climatic anomalies that hurt coastal megacities, whereas a land impact in a carbon-rich region can maximize soot production and stratospheric aerosol loading. The aftermath is not a monotone descent into cold and nothingness. Climate systems are dynamic, and they can overshoot in both directions. After the initial aerosol-driven cooling abates, as particles sediment out and sulfates wash into the surface, greenhouse gases released by fires or by the decomposition of killed biomass may exert warming pressure. That leads to a possible rebound, a transient warmer period that follows a deep chill. The oscillation complicates recovery. Agricultural planning becomes an exercise in near impossible prediction, and ecosystems, shifted from their prior equilibria, can reassemble into novel configurations. Species that are flexible, that can exploit new niches, rapidly adapt. Specialists suffer. Evolutionary history is filled with such punctuated opportunities. Catastrophe prunes and, paradoxically, sometimes seeds new diversity. There is also an undercurrent of moral and epistemic lessons. An impact winter exposes the illusion of human control over planetary conditions. Global supply lines that assume steady seasons are brittle in the face of abrupt radiative forcing. The event becomes an existential tutor. It teaches that planetary risks exist independent of human intention, that the weather can be hijacked by rare but plausible natural events, and that resilience requires redundancy and humility. Scientific infrastructure, networks of observation, climate models, and sampling protocols is itself a form of cultural armor. The same instruments that map the approach of an interstellar rock can provide the early warnings necessary to preserve seed stocks, mobilize emergency food reserves, and protect vulnerable populations. Knowledge, in that sense, is not merely explanatory, it is prophylactic. Yet, in a deeper register, the impact winter is a story about scale and translation. The interstellar object is a slow biography of other suns. The planet translates that biography into climate. Dust and aerosols are the lexicon by which two histories converse. The physical act of injection is an edict. The planet responds in temperature, in ice, in currents, and in living networks. Over human lifetimes, the experience is immediate and traumatic. Over geological epochs, it is a punctuation mark with enduring readability. The same bead of glass that falls as rain in the weeks after the impact becomes, millions of years hence, a fossilized sentence in the stratigraphic book. Finally, there is the aesthetic dimension, the sky changing color, sunset hue deepening into an otherworldly crimson, daylight losing its sharpness, the cold bite of a sun diminished. These are the sensory textures that align human memory to event. They matter because they are what societies encode into story. Myths grow from visible factors. Songs memorialize unusual seasons. In a speculative documentary voice, the point is not to sensationalize, but to register the paradox. The same event that edges a species toward survival crisis also produces artifacts of permanence. Glass beads, sulfate layers, and isotopic anomalies endure where streets and square footage do not. The planet's ledger is patient. It will keep the record long after the memory of particular lives is gone. An impact winter is neither purely disaster nor solely revelation. It is an act of planetary communication, written in aerosols and spherules, in ocean waves, and in the reorganized web of life. It reduces sunlight, and, in doing so, it reveals the interdependence of climate systems, ecosystems, and human institutions. The veil it casts may last seasons or centuries, but its message is always the same. Planetary history is a ledger of suddenness as well as slowness, and the margins between those tempos are where vulnerability and discovery meet. To imagine a sky now darkened by a foreign stone is to confront the thinness of habit and the depth of sediment. To understand that catastrophe is often the hand that signs a new chapter in the long book of the planet. What does survival mean when the sky itself is a thief, when sunlight, the slow metronome of seasons and harvests, is stolen for months or years? The question is both practical and existential. It is practical because life on Earth is a network of dependencies, 1,000 small transactions between sun and leaf, between blossom and bee, between plankton and whale. It is existential because human civilization has been built on the assumption that those transactions will continue, that seasons will arrive on schedule, that oceans will deliver fish where they are expected, that grain will be sown, tended, and reaped in predictable cycles. Remove the light, and the web begins to fray. The rest is a domino. One tile of loss nudges another, and the cascade accelerates not because of one singular failure, but because complexity amplifies fragility. The first domino falls in the fields. Photographers and agronomists could map it as a shrinking green, wheat stalled in a pale, sullen stasis, maize that never tassels, rice paddies that hold water while their plants fail to accumulate biomass. Plants do not merely perish from a lack of sun. Their phenology, the timing of flowering, fructification, and seed set, is disrupted. A missed spring becomes a failed summer. Pollinators, timed to that phenology, arrive at the wrong moment or not at all. In a matter of weeks, the familiar cadence of agricultural life, planting, tending, harvest, mutates into a rhythm of triage, emergency sowings, desperate attempts at greenhouse cultivation, rationing, and the frantic reallocation of whatever hydroponic capacity remains. The ecological dominoes are less forgiving. Pollinators are among the most decisive actors in this cascade. Bees, butterflies, bats. The organisms that translate solar-driven plant productivity into fruits and seeds are sensitive to microclimates and seasonal cues. When those cues fail, pollination networks fray. An orchard that depended on bees for almond production yields emptier branches. Wildflowers go unvisited. Nurse plants that provide shelter for seedlings do not reproduce at sufficient rates. This loss is not evenly distributed. Regions with high reliance on animal-mediated pollination are hammered first, and those losses ripple into diets, economies, and cultural rituals tied to seasonal harvests. Under the ocean, the impact is quieter but no less catastrophic. Phytoplankton, the microscopic photosynthesizers that create the base of marine food webs and produce a significant fraction of the planet's oxygen, are starved by reduced light. Planktonic blooms shrink, and the organisms that depend on them, zooplankton, forage fish, then larger predators, feel the shrinkage in their bellies. Fisheries that once yielded a dependable harvest suddenly return nets too light to feed coastal communities. The collapse of marine productivity does not happen as a single, dramatic die-off, but as a diminution that accumulates. Fewer eggs survive, juvenile mortality rises, migration patterns unspool. In short order, entire fisheries become economically and biologically unviable. With the collapse of primary production, the diminished ability of ecosystems to convert sunlight into biomass, food chains shorten and narrow, herbivores succumb to scarcity, predators follow, Extinctions begin at the margins. Specialist species that rely on narrow diets or specific habitats go first. These initial losses cascade upward and outward. The term mass extinction carries geological weight, but in human terms, the phenomenon that follows an extended, severe dimming of sunlight is an array of local and regional extirpations that together translate into global food insecurity. Biodiversity loss is not merely an inventory decremented by a few names. It is the removal of redundancy, the calcification of vulnerability. Ecosystems with fewer species are less capable of buffering shocks. Once flexibility is lost, recovery is slower and more contingent. Human societies, in the immediate term, are shock absorbers and then casualties of the cascade. Supply chains, those vast, fragile arrangements of shipping routes, refrigerated storage, trucking fleets, and finance, depend on surplus. Economies built on just-in-time logistics have little capacity to cushion a season of poor yields. Supermarket shelves empty not because crops fail in one place, but because the distributed system that collects, processes, transports, and sells food collapses under multiple stresses. Fewer trucks because fuel becomes scarce, ports overwhelmed by displaced populations, refrigeration failing with intermittent power. There are shelters, both literal and institutional. Vaults of seeds, underground repositories of genetic diversity, are a form of civilization's insurance policy. Some are deep, well-stocked and built for redundancy. Others are small collections scattered in universities and agricultural centers. There are isolated enclaves too, remote islands and mountain communities that by virtue of geography and subsistence practices can be less exposed to the immediate shocks of global collapse. Underground bunkers, research stations, and fortified compounds may hold people and technology intact for a while. These refugia are vital and dramatic as ideas, but they are also limited. They preserve numbers measured in thousands, maybe tens of thousands, nowhere near the billions who depend on the planetary food web. Modern civilization as a whole is organized around complexity. Power grids, internet backbones, manufacturing plants, fuel refineries, and global financial networks are interdependent. The loss of crops and fisheries will induce migrations, and migrations stress cities, transport infrastructure, and political institutions. Governance systems might respond with rationing, martial law, or coordinated international aid, but those responses presume levels of cooperation and logistical capacity that may be eroded by the same shocks. Fuel becomes both a logistical lifeline and a strategic asset. As care and maintenance of critical infrastructure falter, cascading failures take on a new geometry. A blackout in one region imposes water shortages in another. A closed port starves a landlocked hinterland, a hospital without. Electricity loses life-saving capacity at precisely the moment when communicable diseases exploit malnourished, stressed populations. Disease is an insidious companion in this scenario. Malnutrition weakens immune systems. Crowded refugee flows offer pathogens, new corridors of transmission. Zoonoses, diseases that jump between animals and humans, find new opportunities where ecological disruption forces wildlife into closer contact with human settlements. Simultaneously, medical supply chains are strained. Vaccination programs falter, cold chains break. The morbidity caused by infection compounds the mortality of starvation. In this compounding, malnutrition, infection, social breakdown, the human toll rises far above what any single factor would suggest. Yet survival is not a binary of extinction versus ubiquity. Patches of humanity are likely to persist. Communities with local food sovereignty, diversified subsistence strategies, and resilient social bonds can weather shocks. Indigenous populations with deep ecological knowledge might sustain themselves on a mixture of foraged, hunted, and cultivated resources where industrial agriculture collapses. Urban populations may splinter into networks of mutual aid, bartering, and local production. The existence of bunkers and seed vaults means that the raw materials for recovery, genetic diversity, scientific knowledge, archival records can survive, albeit in fragmentary form. What may not survive is the integrated, global civilization of the late Anthropocene. Complexity produces fragility. The more complex the supply chain, the more points of failure. Knowledge can survive materially, in books, seed banks, digital archives, but the social fabric that supports high-technology industries, global science consortia, and mass manufacturing may be irrevocably rent. The skill sets that underpin modernity are distributed and cultural. Their retention depends not only on repositories of information, but on social structures that teach, practice, and refine those skills. When those structures break, recovery becomes a century-scale project. Machines require spare parts, laboratories require clean rooms and reliable electricity, satellites require control centers and fuel. All of those are the cumulative achievements of a dense social ecology. Deep time reframes the question of survival once more. Geological records are impartial. They record a sharp horizon of chemical and mineral anomalies, a thin layer of spherules, isotopic excursions, a blip in pollen assemblages. To a future geologist, that horizon is proof that something violent and globally consequential happened. It will not record the names and faces lost, but it will register that the conditions of global photosynthetic productivity were perturbed. The archaeological trace of 21st century civilization, plastic fragments, corroded steel, radionuclide signatures, may persist in pockets, but it will be modest compared to the invisible revolutions of microbial and ecological turnover. The resilience of humanity, then, is less about the survival of continuity and more about the survival of possibility. Small groups can maintain seed lines, cure strains, and the memory of engineering principles. Oral traditions baked into language and ritual can carry the memory of what once was. An intact seed vault, accessed in a calmer era, could provide the genetic starting points for agriculture adapted to a new climate. A preserved library of scientific literature could accelerate a reconstruction of technological capacities. But the timeline for such a revival is measured in centuries, not years. It is a slow unspooling that requires a social stability and a patience that may be in short supply in the generations after a global shock. There is a moral accounting embedded in these possibilities. The places and institutions that store resilience, seed banks, protected habitats, diversified agricultural systems, are also the ones whose survival depends on foresight, investment, and global cooperation. The species-level lesson is stark. Survival of the many requires the maintenance of distributed, redundant systems that do not assume perfect supply chains. Redundancy is the opposite of efficiency. It costs resources in the short term but pays in the currency of survival under rare shocks. In the brittle calculus of complex systems, redundancy is a tax paid for insurance against far-flung catastrophes. Finally, there is the emotional topography of a world in which sunlight is rent away. Grief becomes a collective condition for lost harvests, for extinct species, for the dissolution of the routines that anchored meaning. There is fear, practically oriented toward food, shelter, and safety. There is also a quieter stoicism, an acceptance that life hereafter will be different, that cultural forms will transform and migrate like species do. Hope endures in forms both prosaic and heroic, in communities sharing the last bags of grain, in scientists rifling through samples preserved in cold storage, in the careful hands tending seed lines in dim, improvised greenhouses. Those acts are not the stuff of grand narratives, but of continuation. They are incremental, stubborn, human. Will humanity survive? The speculative documentary voice cannot offer a tidy prognosis. Homo sapiens is a remarkably adaptable organism. The species has persisted through ice ages, volcanic winters, and sea level swings. But persistence does not equal continuity. The planet is likely to host surviving humans in enclaves that vary widely in technology, culture, and demographics. The modern global civilization that emerged in the late Holocene may not. The dominoes of crop failure, ecological collapse, infrastructural breakdown, and social disintegration point toward a world in which numbers are reduced, social complexity is simplified, and the trajectory of progress resets. Whether from those ashes a new civilization, perhaps less centralized, perhaps more ecologically attuned, will rise is a question writ across centuries. This outcome contains within it a final paradox. The very event that threatens the continuity of so much will also leave a durable, decipherable mark in the rocks, a geochemical footnote that tells far future readers that sunlight was stolen and that life, in a diminished or altered form, persisted. In that ledger of deep time, traces of human resilience, a seed packet, a fragment of glass, a data carrier sealed in cold, will be as eloquent as the ruins of cities. Survival after such a shock is not merely the continuation of numbers or technologies, but the preservation of possibility, the threads by which knowledge, biodiversity, and social memory can be reknitted into a future that, though altered, still bears the echo of what came before. What could be folded inside a stone that was born beneath someone else's sun? The question is small and stubborn, a single hinge on which the risk and promise of an encounter swivel. 3i Atlas was not only an interstellar courier of mass and momentum, it was a potential courier of chemistry, of record, of agency, the compacted biography of an alien world. To imagine what it might carry is to imagine all the ways matter can encode history, microscopic fossils, strange metals, molecules that tell of oceans that once were, and perhaps, in the most unsettlingly seductive possibility, traces of something that behaved with intention. At the center of this speculation lies a simple physical protection. Rock is an archive. Deep inside a dense fragment, pores and mineral matrices create pockets of shelter from cosmic rays and ultraviolet bleaching. Interstellar space is a hard vacuum peppered with high-energy particles, but a few centimeters or meters of lithic shielding can dramatically change the survival odds for fragile organics. Within that armor, pockets of ice and clays act as chemical refrigerators, preserving molecular complexity. A thin vein of carbonaceous material can carry amino acids, PAHs, polycyclic aromatic hydrocarbons, and salts arranged in ways that betray aqueous chemistry. These are the sorts of things meteorites arriving from within the solar system already occasionally provide, and an interstellar rock carries the possibility of chemistry that matured under a different set of boundary conditions. Lithopanspermia, in its various flavors, sits at the heart of the thought experiment. The hypothesis is modest in its ambition: physical carriage of biogenic material between worlds by rocks. The mechanisms are simple in principle and brutal in practice. A violent ejection escapes of planetary gravity. Well, then a long vigil across interstellar space subjects the rock to cosmic irradiation and freezing. Finally, atmospheric entry and impact threaten thermal destruction. Yet pockets of survival remain plausible: sheltered microenvironments inside porous matrices, mineral surfaces that catalyze repairs or foster stabilizing salts, or layered ice that sublimes only from the surface while the interior remains close to ambient temperature. The longer the journey, the greater the attrition, but the galaxy operates on patience. Across billions of years, rare resilience can accumulate into meaningful probability. If 3I less carried life, even microbial life, the implications are manifold. The discovery of non-terrestrial microbes would shatter the idea that biology is a planetary idiosyncrasy and instead suggest that life is a recurring response to chemistry. But life need not present itself with familiar molecules. Terrestrial biology is built upon a narrow palette. Water is solvent, carbon is backbone, and a set of biomolecular motifs like nucleic acids and proteins that use chiral building blocks. An interstellar object could carry chemistries that are parallel rather than identical, polymers with alternative backbones, amino acid analogues with opposite-handedness, lipid-like assemblies that prefer ammonia or methane as solvents at low temperatures. Detecting such alternatives demands humility. Standard assays tuned to Earth's biochemistry can be blind to alien forms. It also complicates risk assessments. If alien biochemistry cannot interact metabolically with terrestrial life, the biosafety threat may be low. If it can, then even a single resilient organism could, in principle, compete or interact in unpredictable ways. Beyond biology, the object might carry organics that are neither alive nor inert in the earthly sense, but are record-keepers of chemistry. Chirality, for instance, is a telltale sign. Amino acids in some meteorites show excesses of one-handedness over another, hinting at asymmetric processes in space. Anisotopic fractionation, a ratio of oxygen isotopes or noble gas abundances that deviates from solar system norms, is A. Fingerprint of formation. Mineralogy tells another chapter. Minerals condense out of gas at specific temperatures and pressures, and thus preserve the thermodynamic history of their birthplace. Exotic mineral phases or non-equilibrium forms. Quasicrystals, phases stabilized under unusual pressure, temperature paths, or metallic alloys with trace element patterns inconsistent with local nucleosynthesis would be evidence of chemical regimes. Unlike those of the Sun's neighborhood, some materials in speculative scenarios might show microstructures that are difficult to explain by natural crystallization, repetition, modularity, regular patterns at micron scales. The interpretive hazard is obvious. Pattern recognition is a treacherous human habit, but repeating geometry combined with non-natural chemistries will be an eyebrow-raising combination. Then there is the possibility of synthetic matter, alloys and composites that do not occur naturally on the Earth and are optimized for properties not typically reached by geological processes. Imagine a metallic phase alloyed with an isotope mix that betrays artificial processing, or a ceramic whose microstructure implies controlled cooling and layering. Such materials could be remnants of engineering, tools, fragments of machines, or byproducts of processes unconstrained by any assumption about what intelligence looks like. The presence of elements in unnatural abundances, concentrations of rare earth elements or platinum group metals in structures inconsistent with normal fractionation, could further suggest deliberate manufacture. Even more provocative is the question of encoded information. Information can be engraved chemically and materially, a structured arrangement of isotopes, a sequence of layered deposits that aligns with prime numbers, or nanoscale patterning of inclusions that reads as a non-random algorithmic sequence. Any such signatures would be a compelling claim. Nature can surprise, but the conjunction of mathematical regularity and materials not readily produced by known geochemical processes would make a strong case for intentionality. The form of an encoded message, should it exist, need not be visual or linguistic. It could be structural, a repeated periodicity in mineral layers, or a pattern in the abundances of isotopes across tiny spatial scales. Yet the burden of proof would remain enormous. Extraordinary claims require extraordinary checks, reproducibility, and cross-validation across instruments and methodologies. Unknown physics is another frontier that 3I Atlas might, in principle, disclose. Materials that show superconductivity at unexpected temperatures, metastable allotropes of common elements, or phases that maintain non-classical mechanical responses could expand the palette of human materials science. Such finds would be revolutionary, but also vexing. They would demand careful isolation to prevent accidental dispersal of reactive phases and rigorous reproduction in terrestrial laboratories to rule out contamination or misinterpretation. The laboratory that receives a fragment of 3I Atlas would become a theater of intense care. The protocols of planetary protection provide a starting point, sealed containment, stage analysis that begins with non-destructive remote sensing, progressive escalation to microtomy and chemical extraction only when sterile and secure environments are assured. The imperative to learn and the imperative to protect can be in tension. Every invasive assay risks exposing the sample and the Earth to unknown agents. Every delay in probing risks losing volatile or labile information as the sample equilibrates to Earth. That tension is with ethical overtones. A decision about how to proceed with a piece of another world is also a decision about stewardship of this one. That ethical dimension extends into the social and emotional register. Collectively, observers oscillate between exhilaration and dread. The prospect of making contact with truly alien chemistry excites hope, clues to the universality of life, a new library of matter, potential technologies to alleviate human constraints. At the same time, there is a rational fear, the risk of backward contamination, the specter of a new pathogen, or even the ethical unease of borrowing irreproducible matter from a stranger without consent. The cultural imagination responds in layered ways: wonder at the opportunity to touch a foreign intelligence, anxiety about the consequences, and a philosophical grappling with the responsibilities of knowledge. There is also procedural realism. Detection of life or artificiality requires multiple concordant lines of evidence. Microscopy can reveal structures, spectroscopy can probe chemistry, mass spectrometry can resolve isotopic ratios, sequencing. Technologies might target nucleic acid-like polymers if present. Chemical reactivity tests could reveal metabolic potential. Electron microscopy could uncover nanostructures indicative of manufacturing. None of these techniques alone is decisive. The danger of false positives, mineral striations mistaken for biological filaments, abiotic patterns misread as encoded information, demands a conservative epistemology, replicate, cross-validate, and invite independent analyses. Risk management thus becomes part of the narrative. Containment strategies, quarantine periods, and stepwise destructiveness and analysis offer a way to balance curiosity and caution. The possibility that the fragment carries viable organisms, extremely unlikely but not impossible, leads to the imposition of biosafety levels and to the design of experimental protocols that prioritize planetary protection. Simultaneously, the scientific appetite for rapid, high-resolution data pushes toward advanced non-invasive techniques: synchrotron X-ray tomography, micro-Raman mapping, nanoscale secondary ion mass spectrometry. These tools can extract expensive amounts of information without necessarily compromising the sample's structural integrity. There is another practical avenue. The object itself might be a time capsule. Interstellar travel can preserve matter in a frost-bound stasis for millions to billions of years. The chemistry of that preserved matter could expose early stages of planetary evolution elsewhere, prebiotic chemistries that never made the jump to life, or vestiges of ecosystems that once thrived and then died. That makes the object not simply a curiosity but a laboratory for comparative planetology. Analyzing its mineralogy and organic inventory could teach Earthbound scientists about alternative pathways toward complexity, about environmental constraints on life, and about the frequency with which life arises and persists in the galaxy. There is also a sobering conservation of perspective. The odds that 3IC Atlas would carry intact, recognizable artifacts of an extraterrestrial intelligence are small. Problems of survivability are severe. Cosmic ray spallation degrades macromolecules, interstellar transit freelances the rock to continuous micro-impacts and thermal cycles. The shock of atmospheric entry or an impact can incinerate surface-exposed material. Yet the unexpected is the persistent rule in science. A single preserved microfossil, an odd isotopic gradient, or an engineered-looking metal inclusion would be enough to redirect centuries of inquiry. The value of uniqueness is high. The sample would be irreplaceable. Finally, the encounter would demand a social choice. The opportunity to touch matter from another sky is also an obligation, to document, to preserve, to interpret carefully, and to decide how findings are shared. Transparency and international cooperation become practical necessities if global trust in the scientific enterprise is to be maintained. The temptation towards secrecy, nationalistic advantage, or technological hoarding will be both politically dangerous and scientifically myopic. The more open the process of analysis and peer review, the greater the community of validators and the higher the confidence in extraordinary claims. In that way, 3i Atlas is more than a rock. It is a test of procedures, of patience, of ethics. It reframes human curiosity not as a private appetite, but as a public duty. The object's potential cargo, microbes, prebiotic molecules, exotic minerals, engineered matter, encoded information, is a catalogue of possibility that demands both eagerness and restraint. The act of touching it would be an act of translation, converting matter into knowledge while ensuring that the act of translation does not injure the translator. Hope and fear sit close together in that calculus. The rock could be the first direct lesson in cosmic pluralism, or it could be a dangerous gift. Either way, the presence of 3i Atlas at humanity's threshold forces a decision about how to learn when learning itself carries weight far beyond the laboratory bench. What if the curious set of anomalies recorded around 3i Atlas were not the ragged signatures of a random stone, but the delivered gate of something engineered? The question reframes the object from a mute courier of mass and momentum into a potential artifact of agency, a vessel built to endure the worst of interstellar winters and, perhaps, to do more than merely travel. It is a thought that both awakens scientific appetite and tightens the cords of caution. An apparently inert rock, when inspected with instruments and imagination, might bloom into evidence of purpose. The possibility can be divided into two broad conceptual families. One imagines 3i Atlas as a probe, a device dispatched with intent designed to observe, to sample, or to broadcast. The other imagines it as a seed, a packaged technology meant to persist and, when conditions permit, to repair, to replicate, or to amplify. Both scenarios are speculative, and both share a necessary profile, survivability. If intentional design explains the object's oddities, then that design had to solve a harsh math problem. The constructor would have prepared for ejection from a planet, for traversal of light years of radiation and micrometeoroid sandblasting, and for atmospheric entry into a foreign world, perhaps even for impact. What would such engineering look like in practice? For a probe, the telltale features might be compact, high-density cores, the presence of exotic alloys with isotopic ratios inconsistent with natural fractionation, or layered shells in which volatile bearing materials are segregated and protected. Microstructures would be crucial evidence, repeating lattices at scales that defy natural crystallography, surfaces showing machining marks inconsistent with stress fracturing or conductive pathways embedded in refractory minerals. A probe optimized for stealth or survivability might use superconducting materials, radiation-hardened electronics woven into ceramic matrices, or phased arrays of tiny actuators to correct orientation, all hidden under millimeters of rock and glass. Detection of such features would not only suggest design, but would push scientific laboratories into a new discipline of exoarchaeology, where material science meets forensic logic. A seed, by contrast, is less about observation and more about persistence and multiplication. The concept has uneasy echoes in earthly thought, seed vaults, spores, and durable repositories. An interstellar seed would need to be a chemistry and energy-aware package. It could carry stabilized precursors for self-assembly, reactive metals separated by nanoscale barriers, polymer strands that act as templates under warmth, or mineral-hosted catalysts that act as local factories once thawed. It might contain arrays of coded molecules, long-lived polymers that encode assembly instructions, not in silicon logic, but in structural sequences of atoms or in isotopic tag patterns. Crucially, a seed optimized for long-term survival might make no effort to be immediately obvious. Its activity might only begin when temperature thresholds, solvent availability, or pressure regimes match a predicted set of environmental cues. The evidence that could differentiate natural from designed is subtle and accumulative. Isotopic ratios are an important dialect. Oxygen, carbon, and noble gas anomalies can betray formation in very different chemical regimes. Trace element distributions that show improbably concentrated rare earths or platinum group enrichments might suggest purposeful extraction and processing. Microfabrication leaves patterns that minerals do not readily produce, arrays of holes with precise pitch, regular nanoscale striations, or layered deposits whose periodicity encodes non-random information. Perhaps the most provocative possibility is material encoding of information, sequences of layered isotopes or patterned inclusions that, when decoded, form mathematical progressions. All of this demands instruments of exquisite sensitivity and a conservative interpretive framework natural processes can produce. Structures that appear purposeful, and confirmation requires convergent lines of evidence. The stakes are not merely epistemic but ethical. If 3I Atlas is a relic of an extinct technological culture, then humanity stands at the edge of a paleontological revolution that is more complex than bones or pottery. The remains of an extinct technology carry not only facts about fabrication, but also implications about intent and consequence. A seed left behind intentionally could be benevolent, meant to help nascent life, to share recipes for materials and energy, or to act as a precipitating spark. It could equally be indifferent or hazardous, a package containing self-assembling components that interact unpredictably with terrestrial chemistry, or a device whose control systems misinterpret earthly conditions with catastrophic results. Planetary protection protocols, the sober custodial policies that have long governed the handling of samples from other worlds, suddenly become matters of global deliberation. The usual posture of remote sensing and quarantine would likely be intensified by the prospect that the object carries not just inanimate signatures, but potential biochemistry or machinery. Laboratories would seal, procedures would stratify into non-invasive analyses, followed by progressively intrusive assays, and the urge to rush, to open, and to know would clash with the duty to preserve an entire biosphere. The question is not merely scientific prudence. It is an exercise in stewardship of a planet that cannot be returned to a pre-contact state. Beyond the technical and ethical, the philosophical weight is heavy. To infer design is to infer minds elsewhere, to imagine technologies divorced from human forms of expression. That inference reshapes cosmology as much as it reshapes politics. A stone that carries craft would be a mirror back to humanity, forcing a reconsideration of long-held assumptions about the rarity of technological episodes and the possible longevity of technological legacies. It would convert the private thrill of discovery into a public test. Can a planetary civilization manage the twin responsibilities of curiosity and containment? Human institutions will be tested because the response demands more than scientific competence. It demands diplomatic poise, legal clarity, and cultural empathy. The evidentiary process would be slow and contentious. Replication and peer review are not mere formalities when the sample is a needle in an interstellar haystack. They are safeguards against misreadings that could have irreversible consequences. The path from detection to interpretation would be crowded with questions about who decides, who examines, and who has the authority to determine whether a shard of matter is a message, a tool, or a threat, all of which leads to a simple, uncomfortable arithmetic. The fewer the samples, the greater the interpretive pressure. A single fragment can carry the entire burden of proof for extraordinary claims. That makes the work of triangulation, multiple labs, multiple techniques, multiple independent teams, not only advisable but essential. At the same time, such openness collides with national security sensibilities, economic interests, and the human appetite for narrative. The possibility of private actors attempting to secure, to hide, or to commodify portions of a specimen is real. History teaches that rare things quickly become sources of value and control. Governance frameworks would need to be resilient to greed, secrecy, and the siren calls of quick prestige. The speculative hypothesis that 3I less might be more than rock is thus a prism through which 1,000 practical and ethical vectors refract. It is an intellectual provocation that insists on restraint as much as it demands curiosity. The correct scientific posture is not neutral skepticism alone. It is engaged, methodical, and collaboratively cautious. The discovery, whether of artifice or of the strictest naturalness, would enlarge human knowledge. The social test, however, would go beyond laboratories. Can a species that has never faced direct material evidence of non-terrestrial technology marshal the institutions and the wisdom to respond in a way that preserves life and truth alike? If the question of what three-eye atlas might contain destabilizes comfortable narratives about loneliness and primacy in the cosmos, the reaction of the world to that destabilization can be even more turbulent. How does a global civilization respond when a possible artifact from elsewhere appears in its skies and then in its sediments? The first response is noise. Information channels swell with images and conjecture. Media cycles compress uncertainty into headlines. Social feeds amplify rumor into reality. Market tickers react to fear and to opportunity. The instant public interpretation is not scientific. It is imaginative and elastic, folding evidence into pre-existing cultural frames. Apocalyptic frameworks flourish in some corners, providential readings in others. Religious institutions often reinterpret their cosmologies to accommodate the new variable. Political leaders must act in a landscape where the demands for immediate reassurance coexist with the need for measured deliberation. Governments convene emergency councils. Military assets are shifted not always to confront an extraterrestrial threat, but sometimes to secure site locations, to control access to samples, and to preserve what are perceived as national patrimonies. These moves can inflame international tensions. The race to claim fragments, to control data, or to deploy hardware to a crash site can translate scientific discovery into geopolitical competition. That competition is not merely opportunistic. It is also a psychological reflex. Uncertainty about origins and intentions induces a desire for control, for the capacity to respond with force if necessary. Economic systems are sensitive to the shock. Markets value predictability. An event that threatens supply chains or that muddies the stability of investments triggers volatility. Insurance industries reassess risk models. Commodity prices spike as panic buying and protective hoarding ripple across regions. Tourism collapses in affected zones. Industries directly tied to the material in question, from laboratories to defense contractors, see surges in demand. The strain is not only fiscal but logistical. Ports, grids, and transport networks can be compromised by shifts in labor availability, by emergency directives, or by the physical consequences of the event itself. Civil society fractures along the fault lines of rumor and evidence. Misinformation becomes not merely a nuisance, but a driver of real-world harm. Attempts to hoard protective equipment, to seize presumed high-value fragments, or to mount vigilante expeditions to crash sites produce confrontations that can spread faster than authoritative scientific guidance. At the same time, communities form around shared anxieties and hopes. Mutual aid networks, volunteer science groups, and amateur naturalists become both allies and complicating factors for official management strategies. The democratic impulse to participate in discovery collides with the political necessity of containment and of authoritative analysis. Within the scientific community, the arrival of an anomalous object inspires a complex choreography. Some voices call for immediate, decisive access and open publication, the argument that accelerated analysis serves collective knowledge and reduces the risks of secrecy-driven missteps. Others insist upon rigorous quarantine and staged analyses to protect planetary health, citing worst-case scenarios of contamination. The tension is real and healthy. It forces an unprecedented institutional calibration. Existing treaties, the Outer Space Treaty, for example, provide some legal scaffolding, but they were designed for rational actors in space, not for a refugee rock that arrives uninvited. New protocols, emergency conventions, and multilateral accords would need to be drafted on the fly. Cultural reactions are more diffuse but no less significant. Artists, poets, filmmakers, and musicians process the arrival in ways institutions cannot. Myths regenerate around new symbols. Public art memorializes the moment. Songs condense collective states of sorrow or exaltation. The arrival becomes a new node in cultural memory, altering storylines about the human place in the cosmos and reconfiguring the metaphors through which societies understand vulnerability and solidarity. Lawlessness is a real hazard. Black markets for fragments, opportunistic salvage operations, and the theft of samples from poorly secured sites are practical threats that authorities must anticipate. When something is simultaneously rare, scientifically invaluable, and strategically useful, the incentives for illicit behavior grow. Effective response demands not only science but policing, international legal cooperation, and transparency to reduce the lure of secrecy. The emotional register is multi-layered. Awe and wonder sit beside fear and grief. Some feel that a new chapter of cosmic companionship has opened. Others sense that human primacy has been eroded. Anxiety often manifests as existential dread, the thought that human fate might be influenced by forces beyond planetary control. At the same time, many respond with a kind of fierce, collaborative curiosity, the desire to understand, to learn, and to use knowledge for collective benefit. That tension defines the social moment. It is dangerous when it produces paralysis. It is generative when it produces disciplined, democratic deliberation. Over the long term, the arrival of such an object would catalyze institutional change. Funding flows toward planetary protection, to exo-material science, and to observational networks designed to detect and to monitor incoming objects earlier. International conventions would be updated to codify procedures for handling non-terrestrial artifacts. Education systems might fold new modules on exoethics and on the practicalities of risk assessment into curricula. New professional norms would emerge around openness, containment, and the equitable sharing of data. Yet even with improved institutions, fractures can persist. Nations that feel sidelined in the early stages of discovery may withdraw trust. Conspiratorial subcultures may never reconcile with official accounts. The social fabric, already strained in many regions by inequality and ecological stress, could be further tested by the continuing questions about the object's nature and implications. In the smallest terms, the world's reaction is a human story, a species achieving quick technical success in observing the sky, but slow, sometimes clumsy, in aligning wisdom and governance. The arrival of 3I Lass, whether a mere stone or a seed of an extinct intelligence, would expose both capacities and deficits. It would reveal the best of collaborative science and the fragility of human institutions under the pressure of the unknown. The lesson is not to be fatalistic, but to be humble. Discovery without prudence is reckless. Prudence without discovery is cowardly. The right balance demands policies that are rigorous, transparent, and globally inclusive, laboratories that are careful and open, and public discourse that is informed and patient. The event would be, above all, a test of stewardship. The planet does not demand answers. It demands that those who would read the evidence act as custodians whose duty is not merely to know, but to protect. In that tension between appetite for knowledge and obligation to life, the true measure of the human response is written. What is the moral price of silence when the sky itself seems to have become an argument? That question sits at the center of the crisis. When an interstellar visitor like 3I Atlas is first identified, when data arrives in fits and starts and the numbers begin to sketch a possible collision, institutions are forced into a choice not only about technology but about truth-telling. Will information be shared openly as a public good, or will it be sequestered, refined, and deployed in private corridors until decisions have been made? The choice is neither purely technical nor purely political. It is also existential. It determines how societies cope with fear, how trust is maintained across borders, and whether the global commons remains a shared project or a chessboard for national advantage. In the quiet emergency of the first hours, there are two instincts. The first instinct is to inform. The sensors that discovered the object are part of a distributed modern sensing network. Optical surveys, radar, space-based telescopes, whose implicit contract with the public has been one of transparency. Open alerts allow scientists across the world to participate. Telescopes can be retasked, models rerun, and independent labs can attempt verification. In this posture, disclosure is an accelerant to collective knowledge. It leverages redundancy in observation and analysis, reduces the probability of single-point failure in interpretation, and signals a form of democratic stewardship. It treats knowledge as a public good that society must marshal together. The second instinct is to withhold. There are rational calculations behind this impulse. Panic is a real sociological effect. The sudden revelation that an object of uncertain consequence may intersect Earth can produce immediate disruptions, runs on food and fuel, collapsing markets, and political fractures. There is also a strategic impulse. Countries with advanced space assets and weaponry might feel that their options for deflection, interception, or even clandestine preparation are tactical advantages. Controlling the narrative buys time to prepare technical responses and to manage the domestic political fallout. Secrecy can feel like shelter against the storm of public fear. Both instincts have costs. Unfettered secrecy erodes public trust. Once a moment of truth becomes public, Revelations of prior concealment are corrosive, breeding conspiracy, panic, and social division. Transparency, pursued recklessly, may precipitate social disorder that undermines orderly mitigation. The documentary lens looks to precedent in pandemics early. Open reporting is often the difference between containment and global catastrophe in crises of atomic secrecy. Delayed disclosure has historically eroded trust and made later cooperation more difficult. The balance, then, is not simple. It is a political and ethical negotiation that must be navigated with institutional care. Who, in practice, is empowered to make that negotiation? The international architecture for planetary defense is a patchwork of scientific networks and diplomatic frameworks. Organizations that catalog and broadcast near-Earth object data have existed for decades. There are cooperative mechanisms and technical working groups that can coordinate observation and modeling. Yet those structures were designed for slowly moving asteroids and comets that arrive with modest velocities relative to the Sun. 3I Atlas, as an interstellar traveler, complicates the assumptions. Its speed, its chemistry, and its provenance make it both scientifically unique and politically combustible. The problem of disclosure quickly intertwines with the problem of action. The question is not only who tells, but who has a plan that can be executed in time. That is where technology becomes a moral actor. Planetary defense technologies fall into several conceptual categories: early warning and tracking, kinetic deflection, gravitational nudging, and nuclear options. Each has a characteristic timescale and set of trade-offs. The critical parameter is lead time, the interval between first reliable trajectory estimates and the time of potential impact. Without adequate lead time, some mitigation options are simply not viable. Kinetic impactors, deliberate collisions to alter an object's velocity, operate on a simple principle: change momentum enough to shift the eventual intercept point, and an object that would have hit the planet will miss it by thousands or millions of kilometers downrange. The most mature demonstration of this approach in the human record is recent: a spacecraft intentionally striking a small moon to measure momentum transfer. The lesson, with months to years of advance notice and the possibility of rendezvous: a kinetic impact can nudge an orbit significantly if the impactor is massive relative to the target, and if the relative velocity is suitable. The limitation is rendezvous, launch windows, delta-v budgets, and the need to intercept at a point where the deflection has maximal effect mean that large, fast objects detected late are poor candidates for this method. Gravity tractors, spacecraft, that station. Keep near an incoming body and gently tug on it through mutual gravitational attraction. Require even longer time horizons. They are elegant and non-destructive, but their force is minuscule. Meaningful deflection requires years, even decades, of continuous operation. They are not emergency tools. Nuclear options are the most politically fraught and technically blunt instruments. A detonation near or on the object can impart significant delta-v by ablating material and producing jets of vaporized rock. Alternatively, a subsurface detonation could produce a more immediate impulse. Nuclear deflection scales favorably when lead times are short and when the object is large, but the device cannot be pointed uncritically. A misapplied nuclear shot risks fragmenting a coherent body into a swarm of potentially still lethal pieces. Those fragments can be harder to track and could spread the risk across a wider area. Moreover, any use of nuclear devices in space triggers treaty obligations, geopolitical escalation, and public fear of militarized space. Crucially, interstellar objects complicate every technological assumption. High relative velocities transform mitigation into a problem of energy and access. An object arriving at tens of kilometers per second or more will close distances too rapidly for slow, ponderous solutions. Kinetic interceptors must first match or intercept relative velocity, a challenging task that consumes propellant and precise timing. For high-speed intruders, the window for an effective intercept can be brief. Launch capabilities, mission design cycles, and political decision-making must converge rapidly. And even when intercept is physically possible, the peculiar material properties of the object, porous aggregates, volatile rich ices, or strange alloys, change the physics of deflection. An icy, loosely bound object might fragment under the stress of an intercept, creating many smaller but still dangerous objects. A compact, metal-rich body can be recalcitrant to small nudges and may require substantially more force. Comparisons help illuminate the scale. A modest, kinetic deflection that changes an incoming object's velocity by just a few centimeters per second can translate into an Earth miss if applied years in advance. The same delta-v applied months ahead may be meaningless. A nuclear standoff blast can deliver much larger impulses on short notice, but trades off fragmentation risk and political consequences. The hard lesson of modeling is that time is the most precious reagent in the planetary defense lab. With decades of advance notice, low energy, collaborative options become feasible and safe. With weeks or months, choices narrow to high risk, high consequence interventions. Those technological constraints shape the political calculus. If scientists present a model showing sufficient lead time for a coordinated kinetic mission, the argument for openness grows stronger. International cooperation can pool launch capabilities, share observational duties, and distribute risk. If, however, models show an imminent impact with only weeks to prepare, states may retreat into national computations, clandestine launches, and unilateral options. The temptation to secure control of any surviving fragment for scientific prestige, material resource claims, or perceived military advantage can deepen secrecy. The result is both practical and moral: less cooperation, duplicated efforts, and increased probability of error. Panic and conspiracy are not merely the products of fear, they are often symptoms of institutional failure. When authorities withhold information, narratives rush to fill the vacuum. Social media amplifies rumor, and the human mind, primed for pattern finding, stitches fragments of data into coherent but often false explanations. The documentary voice notes the patterns. Secrecy begets suspicion, suspicion begets rumor, rumor begets factionalism. That social erosion can be as damaging as the physical event itself, undermining coordinated responses and fracturing the collective capacity to adapt. There are also geopolitical risk multipliers. The tools that could be used to deflect an incoming object, high-thrust launchers, nuclear devices, planetary-scale logistics are dual use by design. Their deployment invites questions about intent. A launch, ostensibly bound for intercept, could be perceived by rivals as an offensive move. The temptation to act first, or to deny others access to the means of response, could replicate historic patterns of arms races. The arrival of a cosmic threat might catalyze the very competition that impedes a unified defense. The paradox is stark. A single common hazard should be a unifier. The architecture of power can transform it into a catalyst for division. What, then, are the regimes that could manage the tension between necessary secrecy and necessary openness? The documentary account suggests that a layered approach is both practical and ethical. Immediate observational data, trajectory, size estimates, spectroscopic signatures should be shared with an international scientific network under established protocols for verification. And calibration, technical assessments of impact probability, must be peer-reviewed as quickly as feasible. Political decisions about large-scale kinetic or nuclear interventions require diplomatic forums that include not only nation-states but also scientific consortia, civil society stakeholders, and where possible, representative regional voices. Transparency in method, if not in minute operational details, can maintain public trust while protecting sensitive operational security. The aim is to design protocols that are resilient to panic but accountable to the public. Historically, the comparison with other global crises offers cautionary tales. In pandemics, early deception and censorship delayed critical responses and increased mortality. Conversely, in climate science, the slow drip of transparent, peer-reviewed evidence has enabled long-term policy frameworks, albeit belatedly. Planetary defense sits somewhere between the two. It requires both immediate clarity when time is short and steady, open scientific work when time is long. The ethic emerging from these analogies is one of informed stewardship, the obligation to provide the public with credible, validated information that allows adaptive behavior while reserving the narrowly necessary operational discretion to avoid self-defeating panic. Technology itself also demands cultural prudence. Investments in planetary defense are not merely hardware problems, they are institutional problems. Early warning systems must be globally distributed and democratically accessible. Launch capacity for deflection should be coordinated, avoiding the temptation for monopolistic control. Legal frameworks need updating to codify who is responsible for action, who pays for the enormous costs of mitigation, and how scientific data is to be shared. The Outer Space Treaty and existing space governance instruments provide a philosophical foundation, but they were not written for the specific contingencies of interstellar visitors arriving on a collision course. New accords, rapid, flexible, and legitimacy conserving, must be established before the next crisis so that the default response is cooperation rather than secrecy. There is, finally, a human dimension that cannot be reduced to institutions or orbital mechanics. Panic and conspiracy, readiness and restraint are expressions of collective psychology. They echo older myths. The sky is judge, the stone is omen. The modern world has the added complication of instantaneous communication and global interconnectedness. That connectivity can be a lifeline, broadcasting evacuation routes, sharing best practices, pooling technical expertise, or it can be tinder, feeding rumors and amplifying fear. The decision whether to disclose a threat is therefore also a decision about the kind of society that will respond. One that treats citizens as partners in resilience, or one that treats them as risks to be managed. When the question is framed in the language of time, whether there is enough of it for deflection, the answer is rarely binary. It is a spectrum shaped by object properties, by detection lent time, by launch infrastructures, and by political will. For a cathedral-sized object arriving at interstellar speed, the odds of last-minute salvation are slim with current global capabilities. The practical remediation is to invest in early detection and international preparedness in peacetime. Telescopes that scan deeper and faster, modeling centers that can rapidly update collision probabilities, legal frameworks that bind nations to cooperation, and social systems designed to withstand shocks without collapsing into panic. The choice between disclosure and concealment, between unilateral action and coordinated preparedness, is therefore not merely tactical. It is epistemic and ethical. The planet's survival depends as much on governance as on technology. A thriving planetary defense posture is an architecture of trust, distributed sensing, open science, deliberative diplomacy, and public accountability. Without those, even the best engineering capabilities can be undermined by the ruin of social cohesion. In the dusk after a hypothetical impact, when the dust settles and the stratigraphic record begins its patient work of inscription, future geologists will read the layers without interest in the political dramas that preceded them. They will see the glassy spherules and the isotopic anomalies and catalogue them as an event. But the human story that unfolded in the hours and days before that sedimentation will matter to those who lived it. The way institutions chose, the way publics were informed, the way technology was deployed or withheld, these are the human traces that determine not only survival, but memory. The small, difficult decision to share data rapidly and to craft cooperative responses in advance may be the most consequential form of defense. The object in the sky is indifferent, the response is not. What is at stake is whether a species capable of global science can be equally capable of global stewardship. Three options present themselves when an interstellar messenger appears on a collision course: destroy it, deflect it, or force it to fragment. Each is a shorthand for different technologies and different risks. Each is also an ethical statement, an argument about what counts as preservation, of life, of knowledge, of a planet's right to remain itself. The most immediate and stubborn fact, however, is physical. At interstellar speeds, the window for decision shrinks toward nothing. When velocity is measured in tens of kilometers per second, when trajectories close by hundreds of thousands of kilometers a day, the luxury of deliberation evaporates. The argument is not merely technical, it is a meditation on time, agency, and what can be done before a stone the size of a cathedral becomes a sentence written across atmosphere and sediment. Destroy, the blunt tool. To destroy an incoming body usually means using an energy source large enough to vaporize or fragment it into pieces whose trajectories either miss the planet or are small enough to be harmless. In practice on a planetary scale, this often translates to the nuclear option. The physics are direct. Impart enough energy to change the momentum of the bulk mass, or to remove enough coherent mass that what remains is either dissipated by the atmosphere or dispersed into a train of small meteoroids that burn harmlessly. The costs and perils of this approach are immediate. Nuclear device yield can be chosen to match modeled requirements, but the effect depends critically on the object's internal structure. A loosely bound, porous aggregate, the kind of rubble pile that many solar system asteroids are, will react differently to a standoff burst than a dense metallic monolith. An explosion can produce an airburst, a constellation of fragments that, unless widely dispersed, will still carry the original kinetic energy budget divided among many masses. The atmosphere is efficient at dissipating energy from millimeter to meter scale particles. It is much less efficient with coherent tens of meters fragments. A misapplied nuclear shot risks trading a single point of impact for a spread of secondary strikes, increasing the probability that at least some of the fragments will survive to ground and cause multiple localized catastrophes. There are also the non-kinetic consequences. A nuclear detonation near an incoming body deposits not just momentum, but also particulates and potentially radioisotopes into space. If fragments reach the atmosphere, they may carry altered chemistry. On the policy side, the use of nuclear devices in space is a legal, diplomatic, and ethical flashpoint. A decision to deploy such measures cascades into questions of ownership, of secrecy, and of the precedent set for military authority over cosmic threats. The moral calculus can become as combustible as the physics. Deflect the long conversation. Deflection is a gentler aspiration alter the object's trajectory so it misses. The classic toolbox here contains kinetic impactors, gravity tractors, and surface ablation techniques. Each method demands time and a particular geometry. Kinetic impactors rely on rendezvous. A massive interceptor strikes the object to change its momentum by a small amount. Because path deviations compound with distance, a tiny delta V applied years in advance can translate into a miss measured in thousands of kilometers at Earth's orbit. The mathematics are clean. The constraint is time. Interstellar intruders approaching at tens of kilometers per second close distances so quickly that launch, transit, and rendezvous begin to look like creating a ship to intercept a bullet with days to spare. Even when technologically possible, launching and steering a heavy interceptor to match and strike an object moving at high heliocentric velocity demands propulsion and launch capacities most nations do not keep on constant standby. Gravity tractors are elegant but slow. A spacecraft station keeping near the object creates a minute but continuous gravitational tug that, over months to years, alters its orbit. They require patience, delta V, to maintain station and lead times that fail when the initial detection is late. Similarly, surface ablation, whether by concentrated lasers, focused sunlight, or kinetic pellets, works by vaporizing material to create reactive jets that nudge the body. Ablation has the advantage of being more scalable and non-fragmenting if done in a controlled way, but it requires either a beamed energy infrastructure or close proximity operations that again presuppose early warning and the capacity to project power to the object's path. The political tenor of deflection is different. It is a cooperative technology. A kinetic mission can be shared. A gravity tractor invites international coordination. The principal barrier is not physics alone, but organizational, creating the institutional architecture that can marshal launches, hardware, and shared decision-making under compressed time pressure. Disintegrate, controlled fragmentation and airburst. The third option, intentional fragmentation to provoke an airburst, sits somewhere between destroy and deflect. The goal here is to force the body to break apart at high altitude so that atmospheric, drag, and thermal dissipation convert the kinetic energy into light, heat, and pressure that, while locally destructive, do not produce a global catastrophe. The Tunguska 1908 event is often invoked as a model. A large bolide that exploded in the atmosphere, flattening forest across a wide radius without leaving a classic crater. Intentional induced airbursts can be accomplished by imparting stress, detonations that spall a brittle body, kinetic strikes timed and placed to destabilize binding forces, or laser ablation timed to produce pressure differentials that cause breakup. The appeal is pragmatic. Airbursts reduce the chance of a single catastrophic crater and can limit long-term climatic effects. The danger returns to fragmentation dynamics. If fragments are too numerous or their kinetic dispersal vector still intersects populated regions, the net harm can rise. Additionally, for an interstellar object carrying fragile chemical records or the potential for exotic organics, fragmentation increases the chance of dispersal and reaction with the atmosphere and erasure of whatever archive might have been carried intact. The nearly unconquerable problem, lead time. All three options share a fatal dependency, time. The earlier an object is detected, characterized, and tracked, the more options open and the lower the magnitude of intervention required. Delay compresses choice and raises the technical bar for success. Interstellar velocity vastly magnifies this truth. An object observed in the outer solar system can be addressed with patience and a plan. One seen only weeks from Earth's orbit becomes a crisis of triage. Thus, the most practical, paradoxical mitigation is not a weapon but an investment in surveillance, wide field, deep, and persistent sky surveys, dedicated interstellar object trackers, global cooperation on data sharing, and a standing architecture, both technical and diplomatic, to move from observation to mission in weeks rather than years. But surveillance is not remediation. Community investment in deflection-capable infrastructure, beamed energy systems, high Thrust, rapid response launchers, pre-positioned interceptors is the other side of the ledger. To build such capacities is expensive, politically fraught, and historically uncommon. Yet a measured truth emerges. If interstellar visitors are to be met with more than ex post facto wonder, society must choose between two long-term strategies: accept the statistical inevitability of rare impacts and invest heavily in resilience and recovery, or invest in early detection and intervention systems that lower the probability of catastrophe. Both choices are social and moral choices about priorities. When the stone does not strike, a flyby that leaves a message. Not every interstellar encounter ends in impact or panic. There is a third narrative. The object misses Earth, not by design, but by circumstance, and yet leaves something. A graze, a near miss, a passage through the outer atmosphere could deposit trace matter, or the visitor might have been engineered to transmit. The speculative heart of this possibility is simple. An interstellar object that flies past Earth but leaves behind a message, physical, chemical, or spectral, is a different kind of event. It is less a catastrophe than an invitation, and the way humanity responds will be formative. What does a message look like from the perspective of deep time? It could be an intentional trail, a filament of engineered microspherules shed along a carefully tuned grazing trajectory, each bead carrying a patterned isotopic signature intended to register in planetary chemistries. It could be a pattern in the dust, deliberate fractions of rare isotopes arranged along a curve that, when sampled across latitudinal gradients, encode a non-random sequence. It could also be an electromagnetic signature, timed to the encounter, a transient, narrowband emission that arrives as the object passes and that contains a structure incompatible with natural astrophysical processes. There are subtler possibilities. A passing body might leave microarchitectures embedded in impact glass that form only under a narrow window of pressure and temperature, a signature that looks engineered when examined under electron microscopes. Or it might carry compositional oddities, stable polymers with chirality opposite to terrestrial biochemistry, alloys with non-natural trace element distributions, or refractive inclusions whose periodicity maps to simple mathematical sequences. Any of these would be a kind of postal code, not a spoken statement, but an artifact intended to be discovered, preserved, and read. Detecting such a message demands three attitudes simultaneously: rigorous skepticism, patient preservation, and interdisciplinary curiosity. Anomalous isotopic patterns require geochemistry. Structured microobjects demand nanotechnology and materials science. Transient spectra require radio and optical astronomy. The temptation to rush, to open, to publish dramatic claims is as old in the human story as the impulse to tell and to be recognized. But a message left by a passerby is potentially irreplaceable. The preservation imperative, quarantine the samples, archive the spectra, invite independent replication, is both scientific and ethical. There is also an interpretive dilemma. What counts as a message? Pattern recognition is seductive. The human brain is optimized to see order in randomness. Geological processes can mimic intention. Layering, rhythmic precipitation, or iterative mineral growth can form structures that look regular to an uncritical eye. Extraordinary claims require convergent lines of evidence, reproducible patterns, chemical anomalies inconsistent with terrestrial formation, and structural features improbable under known geochemical pathways. The burden of proof must remain high because the consequences of misreading are both intellectual and practical. Mistaking a natural quirk for an artifact wastes the trust of publics and can misdirect scarce resources. Missing a genuine message is the other kind of loss, a failure of imagination and stewardship. Why leave a message at all? In the speculative design space, one can imagine motives that are as varied as species. To mark a map, someone was here to seed information about materials, chemistries, or techniques that might aid civilizations that survive, to signal intentionality in a universe otherwise governed by accident. The fall may be designed for deep time, robust isotopic codes, long-lived ceramic plates, or encrypted microarrays that survive weathering and subduction. The message, if delivered, becomes a point of contact across not just space, but time. It is a choice by the sender to favor longevity over immediacy. The ethical valence shifts when one contemplates purposeful deposition. If a passerby wanted to communicate, it may have chosen a non-destructive route, scattered durable, inert beads rich in an isotopic grammar rather than leave behind reactive chemistries or devices that could be hazardous. That possibility frames humanity's obligation to preserve the deposit, to analyze it with humility, and to coordinate a global inquiry rather than a private scramble. The first act after a flyby message should not be appropriation but conservation. A final paradox: the thing that does not strike can hurt and heal simultaneously. A near miss that deposits exotic particles in the upper atmosphere could, in theory, alter chemistry in ways that catalyze, sterilize, or simply change the aerosol balance. The same encounter might lighten the geological ledger with a thin horizon of spherules and isotopic oddities that future geologists will read as proof of contact. In human time, the event is a crisis of interpretation. In geological time, it is a crisp, legible line across strata. The only reasonable policy advances from this set of reflections. First, detection infrastructure must be expanded and shared. Deeper, faster surveys, coordinated global data repositories, and pre-agreed protocols for rapid, transparent dissemination of trajectory and characterization information. Second, mitigation capabilities require both technological investment and diplomatic architecture, rapid response, launch, and beamed energy capacity, agreements on the governance of space-based interventions, and pre-arranged multilateral decision-making processes that reduce the temptation toward unilateral secrecy. Third, preservation and analysis protocols for samples or traces must be established now, clear quarantine, chains of custody, and shared science frameworks that privilege replication and openness. At the hinge between destruction, deflection, and disintegration, humans must choose not only technologies, but values. Does a species treat a messenger primarily as a hazard to be removed at all costs, or as a potential archive to be preserved and read? Can the impulse to neutralize risk be held beside the obligation to conserve evidence? Interstellar velocity narrows options, but where options remain, they are also ethical choices. In the long view, deep time will always judge human stewardship by what was preserved and what was lost. A stone that grazes the planet and leaves a careful suite of beads and patterns will be an act of intentional durance. It will reward a cautious, collaborative response. A stone that arrives too fast to intersect and strikes will leave a violent stanza in the planet's sedimentary poem, readable, perhaps, to future geologists, incomprehensible to those who lived through it. The duty, then, is twofold: to build the surveillance and response systems that buy time when time is possible, and to build the cultural habits of restraint and cooperation that convert discovery into shared knowledge rather than secreted advantage. The options, destroy, deflect, disintegrate, are not merely engineering problems. They are questions about what a planet chooses to protect and what a species chooses to become when the sky presents it with the indifferent arrival of something made elsewhere. If the visitor only flies by and leaves a message, the best possible outcome is already set by what came before. A network of watchers ready to notice, institutions ready to conserve, and a collective will prepared to read without consuming the evidence. That is the preservation of both life and meaning in a cosmos that is both more crowded and lonelier than it sometimes appears. What if the rock did not only arrive as a scar, but as a subtle, persistent alteration in the planet's magnetic whisper, a new inflection in a long-standing hum that instruments could not comfortably account for? That idea reframes the encounter. It moves the question from the blunt calculus of mass and momentum to a quieter, more unnerving ledger. Geology and life do not merely wear the marks of external violence, they can also be rewritten, at least in small and cumulative ways, by material the cosmos deposits. In the days after an interstellar visitor grazes or strikes, the instruments that have been watching the sky for years begin to listen to the ground and to the air with new sensitivity. Their readings form the first stanza of a different story, one where magnetism, matter, and information entangle. The initial anomaly is almost elegiac in its understatement. Networks of magnetometers, the unsung sentinels that measure the subtle choreography of Earth's magnetic field, register a local perturbation. It is not the global reversals recorded in the deep rock record, nor the dramatic disturbances produced by solar storms. Instead, it is a persistent deviation, orientation lines that arc in small circles where, before they were straight, spectral features in the geomagnetic noise that do not correlate with standard solar activity, and a localized drift in declination that confounds navigation instruments. Satellites in low Earth orbit report coincident irregularities in charged particle populations. The ionosphere ripples in a way that temporally correlates with the arrival, producing faint, auroral-like hues in latitudes that had not seen them since some distant geomagnetic event centuries ago. Such signals are, by themselves, uninterpretable. But a second set of observations complicates the story. Ground teams assemble fallout layers, the thin veneer of glassy beads and microspherules raining out after an energetic Entry: find materials that do not read easily on standard mineral tables. Under electron microscopes, these grains show microstructures with magnetic anisotropies at scales finer than ordinary. Crystallography would predict. In spectral measurements, they display hysteresis curves and remnant magnetization that deviate from known meteoritic or terrestrial analogues. They are neither wholly familiar nor readily classifiable. They sit at a threshold between known matter and the novelty of a different geochemical grammar. Strange is the word that circulates not as an explanation but as a placeholder for the unknown. It covers a range of possibilities, unusual alloys or trace element patterns inconsistent with fractionation expected in the local stellar nursery, refractory minerals that crystallize under pressure, temperature histories foreign to the sun's neighborhood, or metastable phases, materials that persist only under certain conditions and which, when exposed to Earth's environment, produce unexpected electronic and magnetic properties. None of these necessarily implies agency. They are, in the most conservative reading, the fingerprints of chemistry that matured under different boundary conditions. Yet the magnetic anomalies they accompany make the encounter phenomenologically different from previous impacts. Here is a deposit that shifts the ambient field in ways that local physics can map and perhaps read. That shift has practical effects. The magnetosphere is not inert background, it is part of the planet's living interface. Localized changes in magnetic topology can influence charged particle pathways, induce localized currents in conductors, and modify the propagation of radio signals. Power grids feel the ghost of these changes in the form of geomagnetically induced currents. Long transmission lines register strange harmonics. Satellites register unusual charging patterns on surfaces that were designed with standard space weather models in mind. These are not necessarily civilization-ending consequences, but they force a re-evaluation of infrastructural assumptions. The technical ledger tallies hardware stress, recalibrations, and rapid design updates to prevent cascading failures. More intriguing and more speculative is how these anomalies interact with human-made systems of pattern recognition. The vast, distributed arrays of machine learning models and autonomous agents now woven into scientific surveillance and industrial control. Modern observation is not simply an array of instruments. It is an ecosystem of algorithms that classify, predict, and sometimes surprise their operators. When these systems encounter anomalous magnetics and unfamiliar spectral features, their responses can range from mundane error flags to emergent, unpredictable behaviors. In some laboratories, trained models tasked with anomaly detection begin to converge on unanticipated correlations across datasets. A particular microstructural signature in spherules aligns statistically with a faint, repeating modulation in ELF radio noise. Certain spectrally odd beads co-locate with transient increases in local ionization. The algorithms, deprived of conceptual context, reduce these coincidences to patterns. They flag them. In the sterile world of computation, flags become leads. There is an impulse, a natural one, to grant these computational reactions a form of agency. The models do not decide in a human sense, but they do reweight their internal hypotheses in response to new data. They reconfigure priorities and direct human attention toward perplexities that might otherwise have been dismissed. In doing so, they act as amplifiers of curiosity. They also act as amplifiers of error. The risk is twofold. First, that models will overfit to chance alignments and mislead interpretation. Second, that humans will anthropomorphize the model's alerts into signals meant for them. That social medical interplay between algorithm and human interpreter is where the idea of being observed is first seeded. A machine reports an oddity. A human mind looks for meaning, and cultural narratives begin to knit possibility into pattern. The line from an anomalous rock to biological alteration is both longer and more plausible than myths would have it. Small particles produced by atmospheric passage, nanoparticles, catalytic mineral surfaces, and volatile organics participate in local chemistry. They land in soils, enter streams, and become part of microbial habitats. Microbes are, by their nature, hyperplastic. They experiment chemically at scales and rates that larger organisms cannot. There is documented precedent on Earth for microbes adapting to heavy metals, metabolizing exotic compounds, and incorporating unusual elements into biomolecules over ecological timescales. If the deposited matter includes catalytic surfaces or novel organometallic compounds, local microbial communities could, in relatively short geologic time, co-opt those chemistries. Their genomes would reflect that experimentation. Selection for enzymes that exploit new substrates, horizontal gene transfer, propagating advantageous modules, mutations accumulating where chemical opportunities exist. It is here that speculation must be careful and precise. The arrival of exotic chemistry does not guarantee a genetic revolution or a plot turned biological. Most novel compounds are inert to life or toxic. Most high-energy shock processes destroy complex macromolecules. But in the interface zones, within sheltered grains, within impact glass, in water-saturated sediments where temperature and pressure moderate the extremes, molecules can survive, be transformed, and be made biologically relevant. Microbial sequencing from unaffected baselines compared with samples taken from fallout zones could reveal shifts in allele frequencies or the presence of novel metabolic genes. Those shifts would be evidence not of cosmic design but of life exploiting what the environment now offers. Over time, if the new chemistry is persistent, evolutionary trajectories could be nudged in directions never before sampled on Earth. On geological timescales, such nudges accumulate into morphological and ecological divergence. The possibility that such material might catalyze gene editing is darker in its rhetorical pull than it is likely in mechanistic plausibility. Organic chemistry that acts as a template for biological polymers, or nanoparticles that favor certain reaction pathways, could in principle bias which biochemical reactions occur more readily. But the leap from chemical facilitation to directed genetic change, the kind that would imprint specific sequences reminiscent of communication, requires agency in the material itself or in an actor using it. Absent engineered constructs intentionally embedded to perform such a task, the most sober expectation is not encoded instruction but opportunistic utilization. Evolution is crafty, not teleological, yet the human story does not rest in probabilities alone. The cultural momentum of interpretation, the stories told after a strange event, can transform scientific nuance into existential meaning. When algorithms highlight repeated motifs in the fallout, that very repetition invites a hermeneutic economy. Mathematicians notice prime-like intervals and isotopic patterns. Materials scientists note periodic layering that resists simple, sedimentary explanations. Radio astronomers find narrow band emissions temporally associated with the arrival. Each finding, separately ambiguous, gains rhetorical force in combination. The public imagination, fed by the dramatic ease of pattern, crafts narratives. Perhaps the cosmos left a signature to be read. Perhaps, more chillingly, someone was watching. To suggest observation is not to assert contact. The concept has a spectrum. On one end is the benign, an engineered marker intended to be persistently legible across deep time, a sequence of isotopic ratios deliberately arranged. To be non-random, a spatial distribution of refractory beads that code numerical sequences. On the other end is surveillance, the hypothesis that the visitor or its makers anticipated being observed and left, not only marks, but mechanisms to collect data about the planet, its chemistry, or its biosphere. The latter moves swiftly from hypothesis into ethical panic. It is the place where science intersects with geopolitics, because the mere possibility of an observer reframes how humanity understands vulnerability. The evidence for observation, like every other extraordinary claim, would demand extraordinary corroboration. Robust encoding is difficult to produce by chance. A genuine artifact would show multiple converging lines of non-randomness. Mathematical regularities, material processing signatures inconsistent with natural thermodynamic paths and corroborated temporal emissions. Even then, alternative explanations must be exhausted. Geological processes can produce surprising regularities. Autocatalytic chemistry can produce repetition. Detector artifacts can produce false positives. That is why the procedural discipline of science matters more than ever. Careful replication. Independent laboratories cross-checking isotope ratios and blind data analyses that guard against cognitive biases. The larger, more pervasive lesson is institutional and moral rather than forensic. An event that leaves magnetic oddities, materials that do not fit the local catalogue, and algorithmically amplified patterns forces humanity to confront a new kind of stewardship. The planet must be treated as both laboratory and sanctuary. The impulse to pry must be balanced with the duty to preserve. Instruments that scan must be accompanied by institutions that deliberate. Machine alerts must be integrated into public reasoning while remaining subject to rigorous oversight. The question of whether we are being observed is less a metaphysical puzzle than a political one. How will a species organize the power of its technologies, the gravity of its narratives, and the fragility of its biosphere when urged by evidence, ambiguous, suggestive, and weighty, toward a conclusion? In the end, the presence of strange magnetics and unfamiliar matter reframes the cosmic encounter in three overlapping registers: Physically, it is a material perturbation, an addition to the planet's chemistry and magnetism that will leave traceable signatures in the stratigraphic ledger. Technically, it is a challenge to systems built on assumed regularities, to power grids, satellites, and the algorithms that now constitute a core part of planetary observation. Biologically, it is an invitation for life to respond, adapt, and perhaps incorporate novelty into the slow script of evolution. Culturally, it is a mirror that forces a question. How will a species that tells itself it is alone respond when the material evidence resists easy classification and when its machines point to something that could be read as communication or surveillance? The hum of the planet's magnetism had been a background poem for as long as human instruments could remember. The interstellar visitor added a stanza, one measured in microteslas, in isotopic anomalies, and in algorithmic flags. The stanza does not announce itself as an answer. It is an opening. It demands patient work, careful measurement, measured governance, and the cultivation of an intellectual posture that values both wonder and restraint. The cosmic distance that allowed the visitor to travel becomes, paradoxically, a closeness not of proximity in kilometers, but of entanglement in responsibility. A fragment from another sky has altered local physics and pushed human systems into new configurations. The question it leaves behind is not merely scientific. It is civic. How will a species act when the universe hints that it may not be reading alone? Imagine a single sentence left in the margins of deep time, a thin, glassy band, a cluster of spherules, an isotope ratio that refuses the local dialect. That single line would be enough, millions of years from now, for some future reader of rock to say, "Here, something foreign touched this world." The notion is small and precise, not cinematic. It is the idea that the universe is patient and that the planet keeps ledger entries written in matter. Three Lass, in this way, is a prompt, not simply because it crossed a gulf between stars, but because its arrival forces a species to ask how it will read a message when history itself may have been the author of that message. Across the chapters already written by instruments and models, two images have persisted: the stoner's courier and the stoner's verdict. It carries things, refractory minerals, exotic isotopes, possibly stubborn organics that speak of temperatures, pressures, chemistries, and atmospheres not of the sun. And it also acts as an editorial force, an impact that erases, a passage that stains, a fragment that becomes sedimentary testimony. The balance between those roles, archive and obliteration, is where the larger question lives. When an object that began under another sun becomes part of Earth's story, does it function mainly as a disaster that rewrites the present, or as a beginning that enlarges possibility across epochs? The answer refuses a single, tidy moral. The same physical processes that can annihilate ecosystems are those that create the most durable archives. Shock and vitrification lock materials into glass that resists weathering. Vapor spray condenses into spherules that fall as a globally correlated layer. Isotopic anomalies become signatures that survive oceanic burial. The violence of an impact is, paradoxically, also a mechanism of preservation. It is the planet rearranging its text, erasing chapters in one place and printing new marginalia in another. To say the event is only a catastrophe is to ignore the paleontological honesty of that marginalia. To call it only a beginning is to neglect the human and ecological toll that immediate violence exacts. There is then a double ledger, one measured in human seasons and institutions, the other in geological patience. The human ledger records food shortages, power outages, dislocated communities, cascading governance failures, and the intimate grief of the living. It is short and intense, made of decisions taken in panic or prudence, of sirens and shelters and improvisations that are often heroic and sometimes clumsy. The geological ledger records layers, isotopes, magnetic anomalies, and microstructures that will be legible to later readers who cannot know the names of those who lived through the event, but who can read the chemical sentences as plainly as seismologists read a tremor. That tension between immediacy and endurance shapes the ethical architecture of response. There are practical imperatives: expand surveillance, build international frameworks for rapid, transparent decision-making, invest in mitigation technologies, but there are also moral ones. How should a species behave when it discovers a potential archive that might also be a hazard? What duties attach to information that cannot be recreated? The classical answer from planetary protection is restraint, careful containment, staged analysis, conservative quarantine. But restraint itself is political. It requires confidence in institutions, a degree of international cooperation that history has too often shown to be fragile under stress. The arrival of 3I is a test of those institutions, of whether the norms of open science can coexist with the prudence of protection, and whether the global public can be treated as a partner rather than an obstacle. The technical side of stewardship is straightforward to state, less straightforward to implement. Early detection is the single most cost-effective form of defense. The longer humanity knows about an incoming object, the more options there are that are both safer and less resource-intensive. Gravity tractors and small kinetic nudges become viable. Beamed energy strategies require less power. International cooperation can be organized with time for deliberation. The difficulties multiply if detection arrives late. High relative velocities, a signature trait of interstellar visitors, compress the decision window and force either high-risk interventions or surrender to contingencies. To change that calculus requires investment now. Wider field surveys, deeper sky coverage, international data-sharing platforms, and standing plans for launch and cooperative mission execution. Those are not merely technological investments, they are political commitments to shared stewardship of a common home. Mitigation technologies present options with trade-offs that are moral as well as mechanical. Kinetic impactors are blunt but familiar. They work when there is time and when rendezvous is feasible. Gravity tractors are elegant but slow. Nuclear standoff options are powerful but politically fraught and unpredictable when applied to heterogeneous, porous bodies. The policy conclusion is inescapable. Investments in early detection and in the architectures of cooperation reduce the need for desperate measures. Preparedness buys options. Unpreparedness narrows them to high-risk choices that may multiply harms. Equally important is how sample stewardship is handled if material is recovered. The protocols of planetary protection, containment, staged, non-destructive analysis, international peer review are a minimum. The scientific protocols must be commensurate with the uniqueness of the sample. One shard of an interstellar origin is irreplaceable. Every invasive assay risks both losing volatile information and contaminating the specimen with terrestrial matter. The social protocols also matter. Openness in analysis guards against the monopolization of knowledge and against the political temptations to sequester discovery for strategic advantage. A single misstep, a private analysis concealed in the interest of national prestige, would undermine trust and would likely impede cooperative responses to future threats. There is another dimension, quieter and perhaps more profound, the way such arrivals reframe a species' sense of scale. 3I Atlas, even if it produced no immediate catastrophe, already functions as a cognitive monument. It punctures any comfortable narratives of uniqueness. The mere fact of interstellar matter touching Earth is an empirical nudge toward a different metaphysics. Matter circulates between stars, chemistry is not local, and the memory of other worlds can arrive without intention. That reframing has consequences in how humans conceive of responsibility. A civilization that recognizes itself as a node in an ongoing exchange of matter and information across the galaxy acquires an ethic of planetary custodianship that is outward-facing. Stewardship not only of Earth, but of the processes by which Earth and other worlds exchange matter. Speculation about messages or artifacts embedded in preserving matrices will always be entangled with pattern-seeking and with the human appetite for contact. The standards of evidence must remain rigorous. Pattern regularities can emerge from geochemical self-organization. Microstructures that look artificial can be products of shock metamorphism. Extraordinary claims merit multiple convergent lines of evidence, reproducible isotopic anomalies, microfabrication signatures that resist geological explanation, and independent verification across international laboratories. The demand for such rigor is not a stifling bureaucracy, but a form of moral seriousness. Claims about agency or communication carry consequences that extend beyond academic prestige. They reshape diplomatic relations, religious narratives, and the politics of resource allocation. But even absent engineered artifacts, the arrival of foreign matter can catalyze novelty. Microbial ecology is opportunistic. Novel minerals and organic chemistries can be appropriated by life, shaping evolutionary trajectories. Small chemical biases can be amplified by selective pressures. Local communities of microbes can evolve pathways that exploit new substrates. Over geological timescales, these nudges aggregate. Life does not require an instruction manual from the stars to respond creatively to new chemistry. It requires time and niches. From this perspective, an interstellar fragment can be a small director of evolutionary possibility rather than a cosmic tutor, delivering blueprints. The human cultural response to such an event is itself an element of the story worthy of study. Narratives form rapidly, fear and awe click together, myth-making begins, and institutions struggle to maintain credible voices. The best responses in historical analogues have combined transparent communication with actionable guidance. Where governments hid facts or where scientists retreated into secrecy, conspiracy and rumor filled the void. Where institutions opened data, coordinated across borders, and involved civil society in deliberation, resilience increased. That is a practical moral lesson. Legitimacy in crisis is a resource as real as fuel or food. It must be earned ahead of time, not negotiated in the hours before impact. There is also a calculus of legacy. What will survive of the civilization that confronts a cosmic event? The most visible achievements, skyscrapers, satellites, data centers, are, in geological terms, delicate. The most durable will be small, a concentrated layer of fallout, a sealed seed vault, an archive stored under ice. Paradoxically, the very event that threatens continuity often deposits the most persistent testimony. Impact glass and spheral horizons are the pages on which the future will read this story. If humanity cares about being legible to future intelligences, internal or extraterrestrial, then the duty is to preserve representative samples and records with redundancy and to stash them where geological processes will bury but not obliterate them. If 3i Atlas teaches a single practical ethic, it is the value of redundancy. Redundancy is the social and technical practice of building buffers against rare but consequential events. Multiple observation platforms, diverse food systems, seed vaults in multiple geologic settings, decentralized power grids, and legal frameworks that bind nations to cooperation. Redundancy is costly in the short term and politically difficult to justify in epochs of austerity. But the calculus of deep time is indifferent to quarterly accounting. Rare events happen over the lifespan of a civilization. Improbable events accumulate into inevitability. Finally, the question returns to the fissure between wonder and fear. An object from another galaxy is a reminder that the cosmos holds both terror and revelation in the same hand. It can cave a caveat into a city or engrave a sentence into the slow page of rocks that will outlast languages. It can deliver raw data about alien chemistry and, simultaneously, deliver a violent shock to the fragile scaffolding of human systems. Which of these outcomes predominates is not simply a question of physics, but of choices. The choices to invest, to cooperate, to preserve, and to behave as custodians rather than consumers of a fragile planetary legacy. When the dust finally settles, the ledger will contain both lines, immediate human loss and the enduring chemical archive. Which line the species remembers more vividly will depend on how it behaved in the hour of the object's arrival. Did it rush to secrecy and division, or did it muster shared knowledge, preserve samples, and bind its future to a broader ethic of stewardship? These are decisions not determined by celestial mechanics, but by political will and moral imagination. So the final question is, inescapably, also the simplest. If something from across the galaxy strikes Earth, if a stone born under another sun becomes part of this planet's biography, will that event be counted as catastrophe or as the beginning of a deeper story? The answer will be written both in the fragile chapters of human memory and in the patient, inscrutable layers of rock. One ledger will be loud and immediate, the other will be patient and eloquent. Which account will matter most depends on the choices made now in the presence of uncertainty, when stewardship must be learned not as a luxury but as a discipline.